Hello, Stefan. Can you hear me? Okay, thanks. I will upload my slides to Blackboard first. Okay. I think we have some. Need to close this. So I will upload the slides for today to Blackboard, so you can just you can get access to it. You can download it in your computer. Oh, intelligence. We have lecture 3, but I don't know what was this. Okay, so I need to in fact update this one. So please, download maybe lecture 3 in your computer, because there are some links for some code which we need to play with today. So I will share my screen with you. Okay, maybe I will just share all my screen, because at some point we need to code, but we can start first with this one. So can you see my screen? I mean, last week, I know we didn't finish slides of lecture 2, but we will go back to it. But I guess this week we need to focus more also on artificial neuron perceptron, and try to use it for solving some problems. And we need to start coding in Colab. This is most important. I mean, this is the most important for me, in fact, that we try to work more with Python coding and try to understand, I mean, the concept behind those artificial neurons. So today I will talk about a perceptron again. We talked last time about a perceptron, and we'll talk also about perceptron learning rule. Today also we will talk more about something called it's adaptive linear unit. It's a perceptron, but it's with different cost function and with different activation function and with different learning algorithm. We will use here gradient descent to adjust the weights of this neuron. It's just a neuron also. It's not a neural network, but it's just one unit. We will talk a little bit about feature scaling and the importance of feature scaling for training our models, and we will have some examples. So we will go back again to a perceptron. What is a perceptron? So what is a perceptron? So the perceptron is the basic unit of artificial neuron, and you can classify a task into two classes. It could be positive class and a negative class. And it's up to us to select, in fact. So it could be positive class and zero class. It could be 1 and 0, or it could be 1 and -1. And the choice, it's based on it's based on the activation function. Which activation function we will use? Which activation function we will use? So if you will use hard limb, for example, so the output should be between 1 and -1, and if 1 and 0, and if you will use a symmetric hard limb or step function, the output should be 1 and -1. So anyway, if you want to use a perceptron, you can use a perceptron only for classifying into two classes. So it's binary classification problem. It's binary classification problem. As a decision function can be defined as a linear combination of certain input values, x, and a corresponding weight values, y. So the decision line, as we agreed last time, it's line, and this line, we need to describe it by some values. So it will be omega x plus b, for example, omega x plus b. Omega, it's the slope of the line, and the b, it's the y-intercept. So the line, the decision line, will be omega x, or omega 1 x1 plus omega 2 x2 plus b. Omega, it's the slope of the line, and the b, which is a bias, it's the intercept, it's the y-intercept. So simply, you can just say it's omega transpose x plus b, omega transpose x plus b. And those omega values, it's the weight values which we need to find, in fact. And the b, it is a bias. Omega, it causes rotation of the decision line, right? So omega, it causes rotation. And the b, it causes translation of the decision line. So in this case, you will have more degrees of freedom. So when we change omega values, we can rotate the decision line in my feature space. So I will plot, for example, imagine that we have two inputs, x1 and x2. So in this case, we will draw a decision line. This decision line will be function of omega 1 and omega 2. When you change omega 1 and omega 2, you can rotate the line. So for example, if y-intercept, if the bias equals 0, what will happen? This line must go through the origin. And when we change omega 1 and omega 2, the line will rotate in my feature space, right? If it is in two-dimensional space. So when you change omega 1 and omega 2, the line will just rotate. And when you change the bias value, you will translate the decision line, you will shift it up and down, right? We will take it up and down. And in this case, if you have omega values and the b values, you will have more freedom to classify any problem, right? Because we don't have a problem now, because I have more degrees of freedom. I can just rotate my line, I can translate my line. So in this case, we will be able to solve any problem as long as this problem is linearly separable. So last time we have been talking about about and or, for example. And or, it's linearly separable data set, correct? So it should be possible to find a line which will divide it into two different classes. So we call it linearly separable. But sometimes in some problems it's non-linear and non-separable, for example. So in this case, I cannot use a line to separate it. I need to find a curve or a plane, complex plane or something to separate it, because it's non-separable. So in this case, we cannot use a perceptron. So we can go into two directions. One way is to try to simplify your data set and using feature engineering, for example, to make it separable, or you need to use a neural network, not a perceptron. So the perceptron, it's very simple. It is a basic unit of artificial neuron, basic unit. It's just one unit. And this unit, it can classify any data set into two classes as long as the two classes are linearly separable. It can classify it into a positive class and a negative class, or it can classify it into a positive class and a zero class. So the decision line, the output on the decision line will be 0. It will be positive above it and negative below it. So in this example, for example, in the screen now, you have the if net equal 1, when net is greater than or equal 0, and 1 minus 1 otherwise. So in fact, this is a step function. So this is the step function or the hard limb function which we will use. So in fact, we need to calculate net output. So we need to multiply those weight values by the inputs plus the bias. So we need to calculate this value, and after that apply this function to this value, because we need to decide, is it positive or is it negative? Which class? Is it the positive class or the negative class? So we need this activation function or translation function to make this decision for us. Because when you apply this net value, it will be maybe positive, maybe it will be 0, maybe it will be negative, right? So when we say that it's a net greater than or equal 0, in this case, if 0 values and the positive values will be classified as 1, and the negative values will be classified as -1. And this is what we want to do, in fact, in classification. Because in classification, we need to make decision. We need to say, okay, this one is cat, this one is dog, correct? How can we do this? I just said I need a decision. I need yes and no, black and white. So we need to make decision. So we need to calculate this net value, and after that decide if this one belongs to the positive class or the negative class. How can we do this? We can do this using this transfer function. What is the meaning of omega 1 and omega 2 and omega m, for example? Those omega values, I mean, when we have the plot, I don't have the graph here this time, but when we had the plot last time, you can draw a circle. This is a perceptron, and it has some connections, and those connections are transferring the inputs into this unit, for example. So each input will be multiplied by a weight value. This weight value should reflect the importance of this one. So it could be, sometimes we need to amplify it, sometimes we need to attenuate it. So sometimes we multiply it by very positive value or very negative value or very small value. So this weight value, it will reflect the importance of this input or this feature for this problem. As I gave you an example last time, you want to get a loan from the bank, for example. So we have the age, we have the gender, for example, you have the income, you have education, right? So some of those are very important. When it's very important, we will give it high weight value. When it's not important, we will give it very, very small value. So those weight values, in fact, they reflect the importance of each feature for my problem, right? You want to get a loan, and maybe one of those features is if you watch TV, for example. No, I don't care if you are watching TV or not. Maybe it has a meaning for the problem, maybe it does not have any meaning. So how can we reflect the importance of each variable? By selecting a weight value. So in fact, this weight value, it will reflect the importance of so it will reflect the importance of each input for the problem which we try to solve. So how can we apply perceptron learning rule? We can apply perceptron learning rule first. There are some steps which we need to follow, right? So number one, I have a perceptron, and this perceptron has some inputs. Those inputs are connected to the perceptron by weights, right? And we need to calculate net, because net equal omega x plus p. So we need to initialize those weights. First, I need to initialize those weights to 0 or 2 small random numbers. It's very important because I need to start my calculations. So I need to multiply x by omega plus p. So I need to initialize omega and b. So first, number one, we need to initialize those weights to 0 values. It should be possible, or to, small random numbers. Number two, after initializing it, we will go forward, multiplying. We will multiply omega by x. Yes, Magnus?
I'm just wondering, if you initialize the weights to 0, won't you get nothing out? Like if you initialize all of the weights to 0, you won't have anything to work with. You'll have a dead perceptron.
No, because in the updating process, you are right. When we initialize it to 0, what will happen? The output will be 0, correct? Right? So
Yeah.
so y will be 0, but the target value here, maybe it's 1, correct? And you see in my screen here, delta omega equal learning rate multiplied by t minus y times x. T minus y, it's the error value. So imagine that the output is 0. So the error value here, it will be, if t is 1, so the error value will be 1. So when it's 1, so in this case, I will start updating my weights, because this one will be 1 multiplied by the learning rate multiplied by the input. So if it is 0 or if it is very small value, it doesn't matter for us, in fact, because we will start calculating delta omega, and the delta omega here, it's function of the error and the input. So if the output is 0, so the error will be t minus 0, so it will be the target value, right?
Right, yeah, that makes sense.
So it will be fine. It's okay to initialize it to 0 or to initialize it to small random numbers. But of course, it's recommended to just initialize it to small random numbers, not 0. But we can test it. And I have an example today where we will test it with 0, and it will work fine, right? Because the most important for us is to find the error value and use this error value for updating our weights by calculating delta omega. So we will go forward. We will calculate the output. So first, I need to calculate y. This is the predictions. So y, it's easy. How can we calculate it? So first, we need to calculate net value, right? So we will go back here. We will calculate net. I initialize those omega values to zeros. Imagine. So it will be 0 times x plus 0 times x2 plus 0. So net will be 0. So I substitute this 0 value into this function, activation function. So if 0 will be 1, correct? So now I have an output. So after calculating this output, I will calculate the error signal. So the error will be target minus y. because my class now, I don't know what is the target. Maybe it's 1, maybe it's -1, but the output now it's 0. So in this case, we will calculate a value for the error, and I will use this rule for adjusting the weights. So delta omega will be the learning rate multiplied by the error multiplied by the input. And after calculating this delta omega, I will update this omega. So omega equal omega plus delta omega. We will do the same for the bias, but the input to the bias, it's 1. Do you remember? I mean, the input to all those weights are connecting those inputs to my neuron. But in fact, the bias, it's connecting +1. So it will be the same equation, but it will be learning rate multiplied by t minus y multiplied by 1, right? And the bias equal bias plus delta b. So we just updating, I mean, the weights and the bias using this rule. And we need to repeat this process several times. So update the weights, and maybe you need to adhere, just repeat it for a number of epochs, for example, repeat it until converge, correct? So we need to repeat this one. We need to repeat this process several times. It could be a number of epochs, for example, or you can just repeat it until you are satisfied with the output, right? So now we need to implement it. So I want you to go to Colab, and I mean, in this slide here, you will have a link for this code. I hope. Maybe it's Perceptron. It's just called Perceptron, but I can share the link with you, because we will use this Perceptron for training. I mean, last time we used a Perceptron for classifying. We used a Perceptron. I will just stop sharing, and I will open my Colab here. So I will share my full screen. So, and I will try to open my Colab. Correct. So please just open your Colab, and we have an example. I guess it's called the Perceptron, just a Perceptron. Yes, maybe this one. Okay. Is it correct? Yes. So this example, I can share the link with you. I can put the link in the chat, so you can just open it. So please just open this file, or yeah. Do you have the file now? Can you share the window? Which window? Okay, to full screen. Okay, fine. So I will stop sharing all my screen, and I will share only my code. Okay. So now we have only this one. So this is the Perceptron, and we need to know how to. I mean, there are lots of codes, online code. So you can just get any online code and modify it. So this is a Perceptron, and we need to apply Perceptron learning rule, and we will use Iris classification problem. We need to use Iris dataset. So first you need to import those libraries, right? And after that, it's maybe we don't need this one here. I mean, maybe you can. I don't know what. Okay. So first we need to upload those stuff, right? Import all your libraries, and this is my Perceptron. So the Perceptron, we will start here. We will start here by we define a class called the Perceptron, and we need to initialize number of epochs. Number of epochs. It's I mean, epoch means we train. I mean, when we train a machine learning model, in fact, we train it for a number of epochs, and in each epoch we go through the whole data set, or all, to be more precise, you go through the whole training data set. So we need to define a number of epochs. For example, it could be 100, it could be 10, and we need to define learning rate, right? This learning rate, it should be a very small number, because this is a step with which we will we will train our model, correct? And we need to initialize the weights. You can initialize, I initialize the weights here to zeros, in fact. Do you see? And it's to the number of inputs plus one. Number of inputs because I have, maybe if you have two inputs. So if I have x1 and x2, I add 1 because I need also to initialize the bias. So this one is for the bias. So number of inputs because I have omega 1 and omega 2, but I need also omega 3 or B. So B, which is the bias, I will initialize it here using these weights. So you can just call it omega 0, for example, or you can just call it bias. You can do it in one line or you can do it in two lines. And of course, a training error, I need to define, a vector where we can store training error for plotting later on. Predict. To predict, it's simple. I just need to multiply the weights by the inputs. So I have here a dot product between x and omega. So if the input is x, right? So it's inputs times omega. So it's just a dot product and plus the bias. In fact, so this equation, it's simply omega, it's omega transpose x, in fact, plus p. So it should be omega transpose, I don't know, just omega x plus p, just omega x plus p. So in fact, this is net. It's omega x plus p, right? So it's a dot product of my inputs and my weights plus the bias. So this is net. And when you calculate net, we need to apply it to the step activation function. So if net is greater than or equal 0, the output will be 1. Otherwise, the output will be -1. So it's a step activation function or symmetric activation function. We call it hard limb function, right? And after that, I need to train because, we will go forward for predictions. We will apply those inputs and those weights. We will calculate net. We will apply this net to the activation function. So finally, we will get those predictions, right? I need to train my model. So if you want to train your model, we will train it for a number of epochs. So I decided here's a number of epochs. It could be 10, for example. So I will just, I will have this for loop to go through all epochs. And in each epoch, in fact, we go through the whole training data set. So we have the training inputs, the training labels. For example, I need to define here training labels, training inputs, and the training labels. And first, in first point, I need to calculate predictions. So I will go forward for one example. So it's for each input, for each sample, because the training set here, it consists of a number of samples. So I will pick the first sample and I will apply it to my model. I will calculate the predictions. From those predictions and the labels, I will calculate the error. I will use this one for updating my weights. So the weights, so this one, it's delta omega, in fact. So delta omega will be the learning rate multiplied by the error multiplied by the input. Right? And I will do the same for the bias. So the bias here, it will be this one. So it will be also the learning rate multiplied by the error multiplied by 1. So when it's for the weights, we need to multiply this one by inputs. When it's for the bias, it will be, we will not multiply anything. You can just imagine that it's multiplied by 1, right? Like this. Yeah. So we will run that part, and after that, I need to store the prediction error. So the error will be labeled minus prediction. I will store it here in this error because I need to plot it for the number of epochs. So I will initialize this one error to 0, and I will take the sum across my whole training data set. So error plus equal this error, label minus prediction. So this is my error, and I will store it at the end here, right? The mean value, for example, it could be the mean error, for example, because I need to plot it at the end. If you want to test your perceptron, we need to upload my data set. So we can get the data set from this UCI repository. I can upload it directly here. Last time we uploaded it from a file, but now we have a link. We can upload the data from a link. So we can just run that part. So this is my data set. So my data set, in fact, it consists of 150 examples. 150 examples, 50 for each class, right? 50 for each class. We have 4 features. It's a sepal length, sepal width, petal length, and petal width. and we have 3 classes here. So this one, it's the labels. So now I need to extract some of those some of the inputs. I mean, for simplicity, we will select only 2 because I want to visualize it in 2-dimensional space. I want to plot it. So I want to plot the decision line. So maybe if it is 3-dimensional space, it will be hard for us to visualize. So we will select only 2 features. So I will select feature number 0 and feature number 2, right? Which is the sepal length and the petal length. So I will select this one and this one for solving my problem. And of course, because the perceptron can solve only binary classification problems, so in this case, I will just select the first 100 data points, because the first 100 data points, they are covering 2 classes, iris setosa and iris versicolor. So we will select the first 100 lines, because the first 100 lines are just covering the data for 2 classes, because perceptron can be used for solving binary classification problem. So I cannot solve it for the whole problem, because the whole problem has 3 classes. 50 for setosa, 50 for versicolor, and 50 for Virginica. So I have 3 classes. I cannot solve this problem by a perceptron. So we will select only the first 100 data examples or data points, and I will try to solve it. So X will be the feature vector. So the feature vector, it will consist of this column and this column, and label will consist of fourth one, this one, right? And I will select from 0 to 100. So I will select the first 100 points. I just need to fix, because why here it's text here, iris, Virginica, and setosa, and versicolor. So I need to replace this one with a number, because in machine learning, we need to work with numerical numbers, numerical values. So I will convert this one into numbers using this command. So y will be, so I will just, when it's setosa, it will be 1, otherwise it will be -1. So in this case, when we plot it, it will be like this one. So the first 50 points will be +1, and the next 50 points, it will be -1. 1 corresponds to one class, which is setosa, and -1, it will correspond to versicolor. So I will just run that part. Now we will use a perceptron to find a decision boundary and to separate the 2 classes, right? We need to find a decision line. So we will go back to this one. Remember, this is my perceptron. We defined it. We will initialize. I mean, at the beginning, we need to decide. We need to select the number of epochs, number of inputs, right? Here we will have 2 inputs. Number of epochs, for example, you can train it for 10 epochs, for example. Learning rate, it could be this number or it could be smaller number. And after that, we will train it. So here, I will select, model called perceptron. Number of inputs equal 2. Number of epochs equal 10. Learning rate equal 0.1. And train using X and Y. We have X and Y here. You see, we extracted X and Y. So X will be the features. Y will be the target feature. So we have input features and a target feature. So those features are labels, for example. You can just say X, it's the features, and Y, it's labels. So we will use X and Y for training our model. And after that, we will try to plot maybe prediction error, for example. So just to plot training error. So I want to plot the training error. So we will train it. So now we got this response. So we started by negative error. It was -2. And after that, in the first epoch, and after that, it go to +2. In the next one, it become, this is the first epoch. At 1, it was -2. After that, it become 2. Stay still 2. It go back to 0. It go up again to. It was possible to stop here, right? Because the error was 0 already, but it went back again to 2 and 0, and it remains at 0 for many epochs. And we will train it for 10 epochs. So this is the training error. So this is the main error from each epoch. The main error from each epoch, right? After that, I want to plot the decision line. The decision line. We know the equation. I know the equation of my perceptron. So the equation of my perceptron, if you can see it here, do you see? So the equation of my perceptron, we will get digital Wacom next week. So it will be easy for writing. But the decision line, it's net equal omega 1 x1 plus omega 2 x2 plus b, right? So it's an easy way for plotting it. I do it for simplicity. You can just find the equation of the line. This equation equals 0, right? And if we assume the value of x1, for example, I can find x2. And if you have x1 and x2, you can plot your decision line. So what would be the equation? So you look into this equation here. Omega 1 x1 plus omega 2 x2 plus bias equals 0. So I need to get x2, for example, because I will assume values for x1. So x2 will be minus omega 1 x1 minus bias, all divided by omega 2. So in this case, I can find x2. So here in that part here, I will find the minimum value for x1 and the maximum value for x1, for example. And after that, I will generate values from x1 minimum to x1 maximum using this step. And this is the equation for x2. So when we run that part, we will get values for x1 and x2. And now we will plot it here. So we got this solution. So I have two classes, Setosa in red, versicolor in blue, and the decision line in green. And if you want to change, we can try, for example, to change the learning rate. So if I made it smaller, for example, and trained it, it's the same solution. Maybe we can make it smaller. But it's still, I mean, the same solution. It looks like, so the decision line is the same, in fact. So you can just try to change those numbers, for example, or because maybe we can just make it much smaller. It's almost the same. What will happen if we make it 0, for example? So there is no training, so we will just test it with the random values, which we selected. Oh, no, so look, the error is 100, negative 100. And if you did this, and if you did this, so you see, we cannot find any decision line. We cannot find a decision line. So this is the error. Because this one, the error, it's negative. So it's very important to have, maybe just have very small learning rate and try to train it. And we got a good decision line, which will separate my data points into two different sets, two different classes. You can get those predictions. I need to calculate in how many cases misclassified, for example. So when I do it, it's a 0 misclassified. And if you see here, we don't have any cases. We don't have any red points in this side, and we don't have any blue points in this side. Right? We don't have any blue points here and red points here. So please just, if you have any comment, just open your mic and try to talk to me, please, if you have any questions, or just try to take some time now to open this file and try to run it. I mean, last year we have been using MATLAB, but I guess this year we wish to stick to Python because it will be more practical in the future. I mean, in your bachelor project, for example, you will have, I mean, some years before, and many students, they have been working with large problems. So we had some groups who have been working with huge data set from Stott and Vivassen. So they learned a lot, in fact, in their project. And I mean, it's important to develop skills in Python. So it will be easy for you in the future. So do you have any question, please? You can just open your mic and try to give me any feedback. Do you have any problem for implementing this perceptron? So now you can try different inputs. For example, you just open the file and try different combinations, for example, or even use 3 inputs. But if it is 3 inputs, we need to plot it in different way because we need to plot in 3D, for example. But I can select different inputs. I mean, here I selected this column and this column, for example, as features. Maybe I can select this one and this one, and we will see, is there any difference? So I will change this one. Right, so we have the same classes we are training. So I mean the training error looks different, but also we can converge. It takes 7 epoch to converge. So now the error is 0, which means we are okay. We will plot the decision line. Do you see? It's different decision line and different data, because it's not sepal length and petal length. In fact, it's petal width.
I think I found out why your training error looks the same if you have the same learning rate
Yes.
all the time. Because you are initializing the weights as zeros instead of as random instead
Yes.
of as random numbers.
Yes,
Meaning
correct.
that, of course, if you're using the exact same data set and you use the exact same weights, of course the output is going to be the exact same.
Yes. Yes. So can you try to initialize it with random numbers? So just comment this line and try to, I mean, instead of zeros, it should be I guess, is it correct? It should be like this. We need to import something here. We can just try to run it first. It's working. Okay, so yes, so it's different. And each time, of course, it will be different because we didn't fix the seed, for example, do you see? So the curve now, it's different each time because each time we generate different random numbers, right? So it's fine. If you want to select it to zeros, it's okay. If you want to select it to random values, it's fine. Of course, it's more logical to select it to initialize it with random numbers. Yes, but also we can, I guess, how do we make the seed? Yeah. Okay, so I just added this line here, so we can have both. If you want to initialize it to zeros, if you want to initialize it to random values, it should be okay. So I want to see the weights. We need to print the weights. We need to see the weights, model weights. So is it possible to print it? Yes. Okay, we have the weights here. So do you see? So this one, it's omega 1, omega 2. Sorry, this one omega 0, omega 1, and omega 2. Omega 0, it's the bias. Omega 1 and omega 2, those are the weights, right? And if you run it one more time, maybe you will get different combinations. So maybe you can try in 3-dimensional space. Can you do it, please, and share your screen with me? So I'm plotting here in 2-dimensional space. I use the 2 features, but you can use 3 features. So we will have 4 parameters here. We will have omega 0, omega 1, omega 2, and omega 3. Yes, any input, please?
I was just wondering, is the perceptron class a good template of a perceptron class?
I don't know. In fact, you are from computer science, right?
Yeah, but I was just wondering, is that sort of perceptron class we're going to keep using throughout the course? Or is it going to change after user case?
Yes, we will change. We will use some, for example, sklearn. We will use sklearn, and we will import all those models from Python. So at the beginning, we will try to develop something simple for us to understand, but we will not. I mean, because at the beginning we just need to know how to do it. So we need to know the concept behind it. But later on, we will just import those models directly from libraries. Because I mean, there is no need, in fact, to write a class for each model, for example, if it is already there. So we just need to start I mean, doing it step by step until we understand the concept behind it, and after that we can just import. Because the perceptron, it's in many different libraries. For example, I have it's in sklearn, for example. It's fine and it works fine. So we can use it from sklearn, for example, right? So, but if you want to change, modify, or it's just to understand, because also when we import it from sklearn, we will not write that part here. We will go directly to this. We will start working by our data. So look, so now here, for example, we wrote this one, correct? But when you will use, for example, PyTorch, for example, or sklearn, we don't need to do this part, and we will start directly the pipeline. In the pipeline, we will start with the data. We will import our data. We will plot the data. We will maybe use some pre-processing techniques, for example. Maybe we'll use BCA, for example, and data standardization, for example, techniques. And after that, we will import the model. So we will do something like this one here. We will start from here. So we will import this one from libraries, from packages. Train, test, predict. So it will be the same, but we will start from here, in fact, or from data. So later on, we don't need to do this one. It's just for maybe in the first week or the first 2 weeks, we will do this because we need to understand the concept behind it. But later on, we don't need to do this. Yes, any questions? Did you run your code already? Please try to modify the features and try to, maybe you can do it for example, 4. I can do it, but plotting, we will not plot it, for example, if it is like this one, for example. So now we have a problem here. Okay. So you can select 4 inputs. We have 2 classes. We will train our model. Now we got some problems. Maybe we need to fix things here.
You need to change the number of inputs.
Oh, number of inputs, yes,
Your
correct.
number of inputs.
Yeah, correct. So it should be 4. So now maybe it's much better. I don't know. It goes directly to, because we have more information now. When you have more features, you have more information. And I had this example all time to students. I mean, you have someone who did a crime and the police is running everywhere and they try to find information. So when you give them more information, it will be easy to capture him. But also those information should be, accurate and sharp. And but plotting it in 3-dimensional space, maybe I'm not good in this. So plotting the decision line here, it will be a problem. But maybe we can plot some of those. I don't know. No, because maybe it's not correct, this one. So we need maybe someone to help us to plot it. But also the error is fine. So the accuracy is 100%, in fact. So this one here, it's the error. It's a summation of y minus prediction. If maybe this one is not correct as well, because y minus prediction, maybe it should be absolute value, correct? Maybe it should be absolute value, right? Because if this one is 1 and I don't know if is it np dot. So it's still 0 also. So we need to add maybe absolute value to be sure that you are getting the exact number of misclassified cases. So in fact, here in this one, we try to find number of misclassified maybe cases. Maybe it's not very correct. Maybe I need to count when y equal prediction, right? So so just if you can modify it now, if you can try to plot it, because maybe plotting it here is not correct now. So if you can do it, it will be okay. But anyway, I mean, this is the perceptron, and if you can see weights here, when we use 4 inputs, so should expect 5 parameters. Those parameters will be bias, omega 1, omega 2, omega 3, and omega 4. And when we look into those numbers here, do you see? This one, it's 0.73. So maybe this is the intercept with the y-axis. This one, it's omega 1. It's the one which is connected with the petal sepal length. This one, 0.1. It's the weight value which is connected with sepal width. This one, it's the one which is connected with petal length and the petal width. So we have those parameters. Those are the parameters. And now, if you, I mean, we have this learning rate. It's maybe large value. If you can make it smaller, maybe it will take more epochs. No, it's just it cannot converge at all. You see, it cannot converge at all in those number of epochs. So now it's from -100 to this one. Maybe if this one cannot converge, maybe you need to increase this one, maybe to. Do you see? So it was at -100 for a long time, and after that it went to 0. So it was maybe 20. Maybe 20 is enough, not 100. Maybe 20 will be enough. So do you see? So we stayed for a long time because the learning rate is very, very small. So the step, we use very, very small step. So it takes time. In fact, when the learning rate it is very, very small, it takes time to reach local minimum or global minimum, correct? So this is the global minimum. Of course, it's not, maybe we need more time, right? So maybe we need more time here. We need, because it's not 0 yet, right? We have some error. No, we don't have any errors. But this graph is not correct. So don't worry about this one. But maybe we need more time here. Maybe it could be 30, for example. So when the learning rate is small, so now it's 0, correct? So when the learning rate is small, it takes more time to train, right? It takes more time to train. And when it's large, we are also in a risk of oscillating around the local minimum, right? We have a local minimum. When the step is large, we will just keep oscillating and overshooting, right? So selecting the learning rate, it's hyperparameters. Those hyperparameters are very sensitive. And if you want to be very sensitive, you need to work with your data. Maybe you need to standardize your data set, for example. So anyway, you can just see that we have number of epochs, and in each epoch, we will go through the whole data set. The learning rate, it's a step which we will use, the gradient descent will use, or the algorithm, the step which is the algorithm will use for updating the weights. Because when we go back to this one here, delta omega, it's proportional to the error. It's a proportional to the, so it's a learning rate multiplied by error multiplied by input, right? So the learning rate here, it's a step. If you put it equal 1, what will happen? Maybe we will overshoot. So if you put this one equal 1, it was okay also. So, but do you see? It was very quickly moving from -2 to 2, and after that we went to 0. So it was okay also to use this large number, right? So the learning rate is very important. The learning rate is very important, and the learning rate it's hyperparameter which we need to select. Yes. Do you need some time to work with this example again? Should we take, for example, 5 minutes or 10 minutes break so you can have more time to play with this example, or should we go to the next one?
Quick break sounds good.
So do you want to take some free time, or should we continue? Okay, break. Okay, so we will take break 10 minutes. We will meet at 11:12. We will meet at 11:12, but please, I mean, in this break, just bring your coffee and try to look into the code. And if you have any questions, just give me your question after the break. So see you after the break. Hello. So after the break, if you have any question, please, about the perceptron, you can just ask, please. So we have some notes. The perceptron learning at decision boundaries that can classify iris training subset perfectly. Why perfectly? Because it's linearly separable. So the BLR converge if and only if the two classes can be separated perfectly by a linear hyperplane. So it's very, very important that the two classes are linearly separable. If the classes cannot be separated perfectly by such a linear decision boundary, the weights will never stop updating unless we set a maximum number of epochs or iterations. So if you're, I mean, it's selection. So at the beginning I said it's very, very important to visualize your data and try to plot your classes, because based on this you will decide which model should we use. So if you can see that the classes are linearly separable, in this case, it's a simple. I can just use a perceptron. I don't need to go for fancy models for a simple data set. So visualizing your data set and understanding your data set, it's very, very important. As I told you last time, you need to spend maybe 50% of your time with the data, 50, 60% of your time with data pre-processing. You need to visualize your data, try to understand your data, because based on this, you will select what model. Model selection is very important. Hyperparameters, which activation function should we use? Should we go for sigmoid? Should we go for hard limb? And so on. So after this, we can use a perceptron for classification, correct? But what about regression? We know that machine learning, we can use it for regression and we can use it for classification. So if you will use it for classification, so I need to use hard limit function like this one. This one, hard limit transfer function or symmetric hard limit transfer function. This one, it will classify the data points into +1 and 0. For example, this one will classify into +1 and -1. Right? But for regression, which transfer function should we use for regression? If you will regress, we need to use something like this one, linear transfer function. Because here we calculate net, and after that we compare net with the threshold value. The threshold value here, it's 0. So if net is greater than or equal 0, the output will be +1. Otherwise, it will be 0. Here, the output will be +1 or it will be -1 otherwise. So now the output from my model will be +1 and -1 or +1 and 0. But in case of regression, we cannot use this kind of transfer function, and we need to use linear transfer function. Right? So we need to use linear transfer function and not a hard limit transfer function. There are many other types of linear transfer functions. For example, we can use sigmoid, we can use hyperbolic tangent. In modern days, in deep learning, you can use ReLU or leaky ReLU, exponential LU, rectified linear unit, or leaky rectified linear unit, exponential linear unit, and so on. So the activation function is very important, and we should select this one according to the problem, according to the context. In fact, which problem we are solving? Is it binary classification problem? If it is binary classification problem, we can use this one. If it is a regression problem, we cannot use this one. We need to use this one, right? We need to use a linear transfer function. For example, I mean, the data set which we played with last time, it was about predicting the annual income in terms of years of experience, right? So I want to predict my income next year, for example. I mean, after 10 years of work, what will be my salary? So if you are working in a company, for example, now, you have been working for 2 years, and you need to know, okay, I need to switch career, I need to shift to another company. So you need to collect historical data from this company, and you need to plot, I mean, the expected income in terms of years of experience. So you will have a decision line, we call it regression line, and you can use this regression line to predict what will be my income after 10 years if I will continue here. So you can make comparisons between companies and so on, right? You can select which company I should, stick with. So in this case, it's not classification problem, but it's regression problem. So in the regression problem, we need to get the line because we will use this line for predicting future values, right? But in case of classification, we will get the same line, decision line, but we will classify data points into two classes, one above the line and one below the line. So in classification, we will have also the same line, but we will classify the data points into two classes. The one which is located above it, in this case, it will be +1, and the one which is located below it, and in this case, it will be -1, using this symmetric hard limb transfer function. So we will get the line, right? And all data points which are located above it, it will be +1, it will be classified as +1, and all data points which are located below it, it will be classified into -1. But in case of regression, no, we just need the line. We just need the line, right? We don't need to use this threshold function. I will call it threshold function. We just need to use this linear transfer function. I just need to know if I'm working here for 5 years, what will be my salary? It cannot be +1 and -1, but it should be a number, right? It should be a number. So we will study now something called adaptive linear neuron. Adaptive linear neuron. This adaptive linear neuron, it introduces the concept of minimizing a continuous or convex cost function, maybe because the sum of squared error, for example, between calculated output and true class label. So it's a different version of perceptron learning rule, because perceptron learning rule, it updates the weights based on a unit step function. We use this unit step function. But in adaptive linear neuron, in adaptive linear unit, we use this kind of transfer function. We will use this linear transfer function. And in this case, we can just use this one we can use it as well also for classification. But it can be used for classification and it can be used for regression, but mainly for regression. Because also indeed, classification is regression because we need to get the line, and after that, we need to apply a threshold function to just classify into +1 and -1. So in fact, you will have a model, and this model, okay, so the cost function, before leaving this one, we will have here a cost function. The cost function will be summation of squared error. The cost function here will be summation of squared error. But in case of perceptron, the cost function with t minus y was error, just error. But in this case here, it will be summation of t minus y squared. Why it's squared? It's just to make it convex, right? We need to make it convex, just convex, because we need to reach the bottom of the curve, right? We need to reach the bottom of the curve. So we made it squared to be convex. So this is the model. There is no difference between this one and the perceptron. In fact, we have some inputs. Those inputs are connected to the neuron by weights. So we will calculate here net input. So the net input will be omega1 x1 plus omega2 x2 plus p, for example, right? So we will have the net input. And instead of using a hard limb function here, we will use linear activation function. And the linear activation function, it's something which does not exist, in fact. It's just the input equals the output. So if the input is net, the output will be y. So y equal net. So it will do nothing. So in this case, we can use this one for prediction, right? So here at that point, I have the output y. So I need to calculate the error here. So the error will be half times summation of t minus y squared. And I will use this error value for updating my weights. At that point, I can use this model for regression. If you want to use it for classification, okay, just add this threshold value here. So when we add the threshold value here, I can compare this net value with a threshold value. If it is greater than or equal 0, it will be +1. Otherwise, it will be -1. So it's the same like a perceptron. There is no difference at all between this one and the perceptron, except that we are just using the error from that point. We are using linear activation function, and we calculate the error here, and we use this error for adjusting the weights. So how should we do it? I mean, when we have this cost function, we call it cost function because we need to minimize cost, right? And this cost function, it's error. It's a squared error. right? It's summation of squared error, SSE, summation of squared error. So this is the cost function. And when we square it, it will take this shape, in fact. It will be convex. And when it's convex, if you started at some point here, you must reach this point, in fact. You must reach this global cost minimum. So this one we have in this x in this axis we have omega. We have here the cost value, and the function looks convex. So when you start at some point here or here, for example, after some iterations, you must reach this point at the bottom. We need to reach the point at the bottom here. So we need to find omega star. So omega star, it's the value of the weights which will minimize this cost function. And the cost function, what is the cost function? It's the difference between target values and the output values. So we need to minimize this difference because I need my model to fit my data. How can we fit my data? By minimizing this error value. So when this value is minimum, it means my model can regress, my model can classify. So we need to minimize this function. So this technique, we call it gradient descent. And in this gradient descent, in fact, we update the weights using this formula. It's minus eta multiplied by the gradient of this cost function. So the gradient into partial j by partial omega, or partial error by partial omega. Right? So we just apply this one. It's a gradient descent. In this gradient descent, yes, Magnus?
Just wondering, since you're just using the gradient of the error, does that mean that you'll never actually reach the theoretical minimum?
No, because it's a numerical approach. In fact, I mean, you can solve it numerically. So if you have a function, for example, we can take a function, but next week we will have this digital board, so it will be much easier. So imagine that, I don't know if I have an example here. I will just search, maybe I put some example here, maybe not in this slides, but maybe in the slides from last week. So because the cost function here will be very complex to solve theoretically, right? So this one, it will be very, very difficult to solve. So if you have two hidden layers, gradient descent, we use it to find the minimum without making those differentiation, without finding it, how do you call it? Theoretically, for example, analytically. So imagine that we have a function. I will just give you an example. So we will make it simple. You have a function called omega y equal x squared plus 2, for example. Can you write it, please? So y equal x squared plus 2. And I want to find the value of x which will minimize y. We can make an example now and we can solve it, in fact. So y equal x squared plus 2. And I want to find the value of x which will make y minimum. Can you plot this function y equal x squared plus 2? Should we make a small example? For example, here we can just make can you try, please? Can we try to make simple example? So I forgot matplot. Dot plot, I guess. Matplot. Is it correct? Matplot. Plot. Okay. So we can just make a function. So can you find I mean x? Maybe it's a value between -10 to 10. We need to have a function y equal, for example, 5 times x squared plus maybe 2 times x minus 3.
If you're trying to program now, it's not visible due to
Oh.
you're only sharing your,
Okay,
your
okay,
PowerPoint.
okay. Sorry, yeah. So I will just stop sharing. I will share. It's just a simple example. We need to plot x and y for any functions and try to apply this algorithm, apply gradient descent to solve it. So just a plot. We need to plot this. Can you see my screen now?
Yeah, it's looking good.
It's x label. Maybe it's x. Okay. So this is a function, correct? We need to minimize it. I guess x plot y plot is different. Oh, sorry. This one should be y.
You have a different variable name before show.
Yeah. Now it's fine. Do you see it? Do you see the function?
Yes.
Okay. Now we need. Do you know? I mean, when we look into this function, what is x, which will minimize this function? What is the value of x? Can you find it analytically? Can you find it analytically? So we need, in fact, to find first derivative and put it equal 0. So I will call it dy by dx. So dy dx equal, it will be 10x, correct? Plus 2, right? And then when we set this one equal 0, we can find the value of x. So maybe not this one. Oh, sorry. Anyway, so in this case, okay, my language is so in this case, what is the value of x? What is the value of x? Can you see what is the value of x? (10x plus 2) equal 0, right? It's dy by dx. So what will be the value of x which will minimize this function? So it's 10x equal minus 2. You can just do it like this: 10x equal minus 2. So x equal, it's, I mean, bad numbers, sorry, it's minus 2 divided by 10 minus 0.2, minus 0.2, correct? Correct? So this is x star. Should we call it x star? So we know that this one, it's the optimum value which we want to get, right? Can you open your mic, please, and discuss with me? Just open your mic, please. Let us discuss this problem.
Yep, this makes sense. This is fine. Hello.
Okay. So we have this function and we need to solve this function. So this one will be the value which you are looking for, right?
That's the minimum of the function, yeah.
Yes. Can we do it using? Can you solve it using gradient descent?
You can make the limit, but seeing as you're using a computer, and it's not actually an analytical computer, it's a discrete computer, you can't do it accurately. You'll never actually arrive at the limit.
Okay. So maybe, is it correct? I'm coding sometimes. I forget things.
Yeah,
quickly.
that's good. That's good.
That's correct.
Yeah.
This for loop is correct.
Yeah, that's fine.
Okay. So we will do it just for few steps. First, we need to find the gradient. What will be the gradient? It will be this dy dx, correct? Dy dx equal, we got it 10 times x, but of course we need to initialize x, correct? Plus 2. So this is my gradient, right? But we need to initialize x. So we need to initialize x. So x will be some random number. Random. Is it correct? It will be working like this? Or we need to write here one value. Can you test it, please? So I just initialize the x with some value, and now I will update x. So this is dx, in fact, correct? So x value will be x plus this dy by dx, correct? But we need to multiply it by learning rate. So we need to define here a learning rate, a step. I will call it eta, for example. So eta equal 0.1. And when we use this formula, we need to multiply this one by negative. Do you know why it's negative? Because we need to move against in the opposite direction of the gradient. We need to move in the opposite direction of the gradient.
You might want to pick a bigger x, as now it's going to be chosen between 0 and 1.
Okay,
it's
so
gonna be very
how can I
close.
select? How can I select from a range?
Just multiply it by 100 or 10.
Okay,
So you get a bigger number.
Oh, because the range is from 10 to yes. Okay, it's fine.
It's chosen from a uniform distribution from 0 to 1.
Okay.
So if you just multiply that number by a scalar, you get a bigger number.
Okay. How can we display it in a nice way? Okay, so we will just print the value of x at the end, and also print the value of our function. So our function will be this one. Where is the function? It's this one. It was nice, of course, if we define fy of x, correct? So we can define this one as define y of x, correct? Is it much better? Maybe it's much better now, right? So we just need to print here y of x. I hope that it will be fine. Okay. I have some error here. Okay. So we reached this value, correct? And this is the value of the function. So maybe it's not enough. We need to increase the number of iterations, right? So it could be 15, for example. But if you can simulate it, if you can visualize it, it will be very good. So now we are still the same numbers, the same value. Maybe it's strange. Maybe 20. Why it's the same value? Do we make any mistake? So we started by this, but this value, it's a very large value, in fact. So but anyway, it's not a problem. So we're reaching minus 0.2 here, right? So but we know that theoretically we know that the minimum value it's so this is correct. Yeah. Do you see? Is it correct? Can you please open your mic?
Seems correct.
So we know. I mean, when we solve the problem analytically, how can we do it? we need to find the first derivative of my function and put it equal 0 and find x star. So now x equal minus 0.2. So we can do this one for simple functions, which can be differentiated and solved analytically. But in case of neural network and the perceptron, this cost function will look very complex, right? Because it will be a function of omega 1, omega 2, omega 3, and you need to find omega 1 star, omega 2 3, omega 2 star, omega 3 star. So it will be really very complex. But when this function, it's very simple. This function, it's just a function of x. So we have only one variable. We have only one decision variable. So we need to find the value of x, which will minimize this function. So, so if you want to find the function, so I will just print here x and f of x, right? Because I know that, because this is x. So, I don't know, can we make it like this?
Y of x.
Oh no, sorry. This one should be just like this one. Yeah.
No, it should be
F
y
is
of
not a
x.
function.
Y of x.
Hmm?
Y of x.
Oh, sorry. Y. Yeah. I'm sorry. So this is y of. I used it for f of x. Why is this string? Why I have those numbers too much? I don't know. Maybe you need to clean those values. Why this one is
You're
printing?
printing entire x arrange, NP arrange.
Okay. Yes. Because we don't need to have this here. I will just put it down here, right? Okay. Because maybe also plotting. We don't need to plot here. We can just plot down here. Right. And so this is my function, right? Which we need to solve. And analytical situation will be like this one. So I will just find the first derivative of the function, set it equal to 0. And from this one, we can find x equal minus 0.2. Print. So this is the analytical solution. Do you see here? It's minus 0.2 and the function equal minus 2.4. Okay. Okay. So now we will try to solve it using gradient descent approach. So we will initialize x by some random value here, right? It's minus 0.89 something. And we will run this one maybe for 10 epoch or 10 iterations. So we will find the gradient. This one, it's a gradient, right? We will calculate the gradient and so delta x will be minus eta multiplied by this one. And we will repeat this one several times until we update x. So we will run it now. It's I cannot understand what is. Why I'm having those numbers? Why?
They're your x. They look like x at least.
Hmm?
They look
because
like
it's not
x.
multiplied by 10. When it's multiplied by 10, they print it 10 times or what?
No, random. The NP random.
Just under your.
Can
x
we run?
equals-
Can we generate random from a range?
No, this is okay, but under x equals NP arrange minus 10 to 10, you print no, you don't print, you plot.
Is this one only for plotting? So this one should be fine, right? It was working, right? Okay, we can just, maybe it's, I don't know. Is it coming from here? No. Okay, why is this one was printing those lots of many things? Anyway, so this is the solution, right? Do you see? This is the solution which we got analytically, and when we solve it, when we solve it using a gradient descent, we got the same solution, right? We got the same solution here, x iterations. So this graph, it's a very simple one, so we can solve it analytically. But if it's two-dimensional, in two-dimensional space, if this one function of x1, x2, x3, x4, it will be more complex. And in artificial neural network, maybe you have 150 weights. So the function will really very complex, and it will be like a mountain. You know, when you go for hiking, you go to the top of the mountain and you want to go down, right? So I need to go down. So it's hard to have a differential equation describing this mountain, but it will be easy to solve it using a gradient descent or gradient ascent if you want to maximize. Yeah. So okay. So maybe I can call it x star, for example. So I can just say it's x star because this is a equal x. Sorry. And here we print x star, and we have here, and also we can plot it here. No, why you cannot is not defined. Yeah. Okay. So do you see this is the point which we want to reach? But please, if you can, I don't know if you can put the graph inside the for loop, so we can, if you can make it, I mean, more visual, so we can see how the gradient descent is moving as a step size. So we can reach this point in 10 steps, maybe less. Is it okay? So this is the point which we want to reach. And there's a eta here, it's the learning rate. So we start at some random point here. If we can plot also this random point, I will call it x rand, for example. So I will just make more line here. So I want to show you from where we started. So this one will be rand, and this one will be rand. Maybe this one will be green circle, for example, right? So I cannot see it. Okay, x rand not defined. Oh, it's called. So, but I mean, we started from very close point, in fact, here, and we reached. Maybe we need to make it much bigger, so we can multiply. Do you know how can we generate random number between two values? I mean, from, for example, -10 plus 10. I mean, integer value, for example.
If you want an integer value, I would say that you just take a regular random value. Like if you want it between -10 and 10, you do random times 20, floor it, and then, or ceiling it, I'm not entirely sure.
But there is function. There is function.
I wrote an example in chat. Random randint, and then pick a range.
Yeah. It's.
I wrote it in chat. You can just use it.
Okay.
If you want. But yeah.
You put it in.
Yeah.
Rand int, for example.
You might have to import the library though. But
this.
It gives you an integer
This
in
one,
a
maybe.
range.
This one.
Yeah.
Import random.
Yep. And then use this one. I think that should work.
Okay. So import random. Yeah. So So we can just put it here. Oh, sorry. Not this one. So this one will be start, stop. Okay, it could be like this. So now we are starting at some point here. So look, we started here and we reached, so we started at the green point and we reached the red one. So in perceptron, in fact, in artificial neural network, we will do the same. But here it's a simple because the function here, it's function in one variable x. But imagine it's all time positive. Okay, now it's negative value, right? So each time you will get, but each time we will reach the bottom, right? Do you see? We are starting from here and we are reaching this point. So I will upload this one also to we can send it to GitHub also, so you can just okay. So is it okay? Do you feel this example was good example? You can change it. You can change the function. You can select more difficult function, for example, and you can see how it will look like. And it's a good example because it helps us to see the difference between analytical solution and numerical solution. So we have the function. We just select any function. We differentiate, and then when you differentiate this one, you just set this one equal to 0. From this one, we can find the x star quickly. This function is very simple because it's a function of one variable. But when it's function of x1 and x2, it will be really more complex. So we need to find partial y by partial x and partial x1 and partial y by partial x2, and it will not be easy, right? And imagine if you have a perceptron like this one, you have a perceptron and it has 4 inputs. So I need to find the differentiation for x1 and for omega 1, for omega 2, 3 and 4, right? So it will be not easy. So, but this example, it's a very simple one. We have a function, we can solve it analytically and find the minimum value, and we can solve it using gradient descent. Gradient descent, it's very simple. I need to calculate the gradient, and of course we need to initialize it. So we initialize it by some random value, right? And after that, we need to select the learning rate, eta. This one, it's the learning rate. And put it in a for loop because we need to repeat this one several times. And in each time, we will update the x value. So we started at, we selected point here by random. And by steps, we will go in steps. If you can, I don't know if you can do it. If someone of you can help me, in fact, to do it, it will be great. If we can visualize. If we can have this graph, it will be really very good. So we need to have the graph inside the for loop so we can see how x is moving, the updates, how much updates. So we start at that point. So the gradient here, in fact, will be negative because we need to reach here. We started at -10, right? So, and I need to reach 0, almost 0. So in this case, we will calculate the gradient at that point. The gradient at that point, it will be negative because it's 10x plus 2. Imagine x is 10 minus 10. So it will be minus 100 plus 2, it will be minus 98. So it's negative. Minus 98 multiplied by negative 0.1, So we will move here at the beginning by very large value, which is almost a plus 9.8 something. So we will move by plus, so x equal x small, x minus 10 plus delta x here, it will be plus 9.8, right? So we will move one step here. We will repeat it until we reach the minimum value here. And if you are starting here also, what will be the situation? Here x is positive. So the gradient here will be positive, in fact. The gradient here, it will be positive. So when we multiply it by negative, we will move against it. Right? So we move against the gradient to reach the
Someone's put in the chat a way to plot in real time so that you can see the change during the loop.
Yeah, can you do it?
Someone's put in chat a link to Stack Overflow.
Okay, you put it in already there? Do you have a link?
Just look in the chat.
Okay, so someone did it already. Mm-hmm. Okay. Yes. Oh, this is very good. But is it working or not working? Oh, he need to use this. Okay. Okay, so maybe I can do it after the lecture, for example, because I'm not sure that it will. It could be, maybe square, for example. I don't know. So it will be plotting this one. But we need to have this plot at the beginning, right? So in this case, we need to have this one. I don't know if it will work or not. So no, we have some error, in fact. X star is not defined. Okay. Maybe okay. So we don't need to plot this one. I don't know if not defined. We have some errors also. The problem it's I don't know if we need to plot this one in. So anyway, maybe someone can try to do it. No, it make lots of plots, I guess. So. So maybe someone can try to fix it, please, and he can share his solution with me. Maybe it will be much. Okay. So maybe Magnus, can you help me to do it later on?
I'm not quite sure if I can help you. I'm not. I'm just the one. I'm just the messenger, just telling you that it exists somewhere.
Yeah, but we can try. I mean, we can try to fix it, so we can just see how X is moving. But the idea behind this simple example is to just to see how can we use gradient descent to update X values so we can reach the minimum value. So if you have any function, you can solve it analytically and you can solve it numerically using a gradient descent. In artificial neural network, it's impossible to solve it analytically. But using those simple examples, it's okay, right? But of course, a gradient descent, it has a problem that if we have here global, this one, it's a global minimum, but sometimes we have local minimum and a global minimum. So maybe we can stuck in the local minimum. It will be a problem. So maybe we can stuck here, for example. I guess I have an example, maybe from last year. I will try to search for it. So it's a function which has local minimum and the global minimum, right? So when the function has global minimum and local minimum, it's very tricky because maybe you can stuck in the local minimum. There is no guarantee that you will reach this one, because in reality, I mean, the cost function of the error here, it's not very smooth like this one. This one looks very beautiful, right? This one looks okay, but it's not the case, because sometimes it's bumpy and it has some local global minimum and local minimum, local and global minimum. So we need to reach the global one, not the local one. But also there is no guarantee. So there is no guarantee that you will be able to reach it. But there are some methods which should be used for, I mean, helping you. Okay, so if you don't have any questions, should we go to the slides? So we will go to my slides again. So now we have this adaptive linear neuron, and it's like a perceptron. There is no big difference. It's the same. We will use gradient descent here. So we assume that the cost function looks like this one, but it's not the truth, right? We assume that it looks like this one, but it might be more complex than this one. And we will initialize the weights. When we as we see in the example, when you initialize the weights, maybe you can start from here, maybe you can start from here. We calculate the gradient, and we will move against the gradient. So when it's positive, we will move against it. And when it's negative, we will move with it, in fact, right? So until we reach this point. And that is why we have this negative sign here. We have negative here because we need to move in the opposite direction of the gradient, right? And this eta, we call it learning rate, and this is the step which will be used for, I mean, moving. We will move in steps from the initial value until we reach the weight, which will minimize this function. So this is the cost function. This is the cost function which we need to solve. We will use this rule, omega equal omega plus delta omega. We need to calculate delta omega. So delta omega will be minus learning rate multiplied by the first derivative of this cost function. It will be partial j or partial e, for example, error by partial omega. How can we get this one? Using something called a chain rule. Chain rule, it's simple. I want to find partial j by partial omega because I want to adjust omega. By the way, we will do it for each omega, right? We will do this one for each omega. So it will be like, it will be partial j by partial omega. It should be partial j by partial y, because there is no connection between j and omega, in fact. This one, it's function of omega through y. So it will be partial j by partial y multiplied by partial y by partial omega. Partial j by partial y, this function, it will be 2 times half multiplied by the first derivative of what is inside here. So the first derivative of t will be 0. The first derivative of minus y, it will be minus 1. So it will be minus eta multiplied by negative summation of t minus y. So that part, in fact, it's a partial j by partial y. multiplied by partial omega by partial j. What is omega? Sorry, what is y? Y, it's omega multiplied by x plus b, right? Omega, sorry, y, the output here, in fact, it's omega x plus b. So partial y by partial omega, it will be just x, because b is constant. The bias is constant value, and omega x, partial omega x by partial omega, it will be just x. So this one will be multiplied by x. Is it okay, this equation? I guess any question, guys? Do you have any question for this one? Do you have any question for this mathematical part? Okay, so if we need to train my model, what should we do? I mean, it's something training mode, batch gradient, mini batch gradient, stochastic gradient. We will talk about it later on. It's not a problem, but I guess we should go for an example. We need to go for an example. You have the link. You have this link. I mean, it's called adaptive linear unit. I can try to open it. So this one. So you cannot see my screen. So can you see my screen?
Sorry to interrupt you.
Yep.
When I click on the link, I get the web page. This is not the web page you are looking for.
Not web page. Okay.
Yeah, when I click on the link at the presentation.
Yeah. Because it's written twice here, I guess, right? I guess it's should be like this.
Yeah, okay. Someone shared it in the chat. Thanks.
Okay. Okay. Yes. Yeah, I will put it in the slides. Maybe it was. Yeah, this is a GitHub one, and so you have it in there. Okay, so now we have this code, and it's for implementing this. Adaptive linear unit, and we can go through it. I mean, this first part, it's the same. This one iris dataset, we just upload it from UCI repository. It's the same like last time. We extract X and Y, right? We did that last time. So we just make some changes here in this class. We just make some, I mean, the rest will be the same. In fact, the rest will be totally the same, except here. So what would be the difference between this one and a perceptron? In fact, the difference will be in the updating here. So first, this is, we calculate net, right? It was the same also. There is no difference. We just replaced it with the linear activation function, y equal net. So we used here the linear activation function. This is the only difference. Right? We just used here y equal net, linear activation function. We calculate the error, and we use this error for adjusting our weights. So if we can go to, to the slide one more time, to this mathematical part, it's delta omega equal learning rate multiplied by t minus y multiplied by x. it could be t minus y, and it could be summation of t minus y. I just need to answer. Oh, sorry. So okay. So did you run the code? So it will be the same like a perceptron, except here we calculate error. We just replace linear activation function. In perceptron we used hard limb activation function or unit step. Here we use linear activation function. We calculate the error. We update the weights. Here we just multiply error by input dot product, because we have two inputs. Multiply this two inputs with error. Okay, we do it in fact in batch learning. We do it batch gradient descent here. So this one will be vector. In fact, this one will be vector. So we will revise this part for training. So we have x and t. X equal training inputs as a vector, right? So x equal training vector. T equal the labels as a vector as well. We will initialize the weights by some random values. In the first epoch, we will calculate net for all inputs, right? So net equal dot product of x and weights. So this one, it's 2 times 100 points. So x here, in fact, it's 100 times 2. What is the size of x? The size of x, it's 100 examples, 100 rows times 2 columns. So it will be multiplied by 2 because we have here 2 weights, omega 1 and omega 2. So 200 values times 2, we will get 100 value. We will get 100 values plus this value. So the size of net, in fact, it will be 100 times. It will be a column vector of 100 elements. So y equal net. We will calculate the error. So it will be target values minus y. Target values also, it's 100 labels. Do you remember it? 1, 1, 1, 1, minus 1, minus 1, minus 1. Minus the y. So we will calculate the error here. We will use this error vector for adjusting the weights only one time per epoch. So when we adjust those weights, we will multiply this error by x. We will multiply this error by x, and we will take the mean value of it. So we will use this value for adjusting the weights. In fact, I need to check. I need to check the size of this one. What will be the output from this net product? Dot product. So so if I can print, I don't know, maybe error from 10 values, for example.
Question.
Yeah.
Why are you just saying that y equals net? Why don't you just use y or net everywhere? Why do you use both of them?
No, but I just here to because in the graph, do you see the graph which we used here?
Oh right, it's a linear activation. Yeah.
Linear
never mind.
activation
Sorry,
function. Yes.
I didn't read the comments. Yeah, you're right.
Yes.
I get you.
It's just linear activation function. Of course, you can avoid it, but I just put it. I mean, it will do nothing. but I just put it here so people know that we still have an activation function and we call it linear activation function. I guess, do you see my screen? Okay, so just run it, please, and let me know if you have any. And I just need to be sure that dimensions are fine. I'm not also. I want to know how this one will work. Okay, we can just select here maybe one epoch, maybe two, maybe one is okay. So we have 100 data points. Okay. I guess we have some problems here. I don't know why. So those are the error values. Do you see those error values? Do you see this vector? This one, it is the error. And this is the input. And when we multiply it, dot product, we will get those two values. So I want to understand how dot product is done in. Yeah, because it's 1 times 10 multiplied by 10 times 2. So the output will be 1 times 2. So it's correct. So this one will be the value here, which we will get from dot product from this one. And we will take the mean. I don't know, is it, we should not use mean value here, in fact, because it's just two values. So I guess that we don't need to use, maybe it's not correct to use a mean value here. So I will just remove it at the moment. I just used the 2 epoch, so maybe you need to increase it to maybe 10. Yeah, so it will look like this one, and this is a decision line which we have. And of course we have lots of problems here. Do you see? I mean, it's not good enough solution, right? We have misclassified points. We have some points which are misclassified. So maybe if we increased, I don't know, or decreased this one, for example. No, sorry, we should not do it. Maybe we need to increase this learning rate. No, it's diverged now. Do you see? So now it's totally wrong. So the accuracy now will be 50% because, I mean, the data set it's 50% one class, 50% the other class, and when we increased the learning rate, we got lots of problems. In fact, still very high. So we cannot converge. We diverge. So we need to use smaller learning rate. So it will be like this. So so maybe you just need to train it for a longer time. Maybe it should be 100 epoch, for example. Because the problem here, in fact, we update the weights only one time each epoch. So now we got a good solution. Can you please open your mic and tell me if you have any comment? Any question, please? Now it looks. So any question? Do you have any question? Any question, please? Do you think it's fine, that part?
It all looks fine, yeah.
Okay.
Sounds good.
Okay. So so if anyone has any questions, just please share it with us so we can. I mean, we can understand. Of course, the model. This is the cost. Model cost. We defined it here as a cost because we need to just for plotting. So in fact, the cost will be half times error square, the summation of error square. So we have this error as a vector, we square it, and after that we take the sum and divide it by 2 to get the cost. We do it for each epoch, and we store it in this variable for plotting. So we have at the end model cost. Weights, we have those model weights. So those are the weights which we have. We have 2 inputs. So this one will be the bias, omega 1 and omega 2, right? Bias, omega 1 and omega 2. And those are the predictions. You can just play with it and you can get lots of stuff. And so maybe we can just comment. Oh. Okay. So and when you run it each time, you will get different results because we have different initial values, right? So each time you will get different solution because we get different initial values each time. So at the end, we have a decision line, which is a green line. This is a decision line. We have the blue class and red class. So now we are training the model using historical data. Imagine we are just collecting data, and I trained a model because I don't know. We don't have any expert who can differentiate between Setosa and Versicolor, for example. So we will collect historical data. We will use this data for building a model. And after that, someone will make measurements, and he will just put it in this 2-dimensional space, and he will see if it is above the line or below the line. So in this case, we build a system which can help us to classify this iris dataset. We can do it for many applications. I mean, for example, you apply for loan to the bank, and the bank has historical data from 1995, for example. And those data, it's like this one, red cluster and the blue one or green one. Red, below the line, they will not get the loan. So we apply, but we don't get the loan. We got rejection, right? So they store all information in the bank, in fact. They don't delete this information. So when you apply for a loan and I have been rejected, I'm not able to get a loan from the bank. So in fact, I am a data point. I'm an example. I and the rest of the people who are applying, some of us can get a loan, some of us cannot get a loan. So at the end, it ends up like this one, two clusters. Red one, who cannot get a loan, and there may be green one or blue one who will be able to get a loan. So this is the historical data. So in the bank, they will build a system or machine learning model because those data has been collected by domain experts. I mean, you go to the bank, you apply for a loan, you provide all information, X1, X2, X3, X4, right? So they collect all information from me. So someone there, he is clever, he will just look into the number and he will say, okay, you cannot get a loan from us. Now he put me in this red cluster. Someone else, for example, you will go to apply for a loan from the bank. You will provide the same information and you will meet someone in the bank. You will say, okay, you will get a loan from the bank. So you will be in the blue cluster. So this is, we call it historical data. So imagine those people in the bank who are very clever. They just got retired and they don't have anyone with the same knowledge. So we will use this historical data for building a system to automate this classification problem. So they will use historical data, Excel sheets, and all those data from many years, and they will use it for building a perceptron, and they will use this perceptron for making this classification problem. So at the end, the perceptron will generate this decision line, and imagine next week, I will go to apply for a loan from the same bank. I provided all my information. They will send all those information to the perceptron, and the perceptron will put me here. So in this case, I will not be able to get a loan. So in fact, we build those models for making decisions or for automating decision making. And just imagine how much money they can save. And that is why people are afraid from AI and machine learning, because they feel that it can take jobs from people, right? Because now instead of hiring those people in the bank who will be sitting in their offices, I mean, working with Excel files and look into your information and make decisions, we don't need them anymore. We can just have a perceptron and the perceptron will do it for us. And imagine that we have a bank on Ålesund, we have a bank on Oslo, we have a bank in Trondheim. All those banks, they will merge those data together and they will build a universal system on Norway, for example, who can make such decisions. So you can just apply your information to the website and they will just say, okay, he should get the loan, he should not get the loan. If he will get the loan, maybe he will get your loan in 1 hour. So it's much quicker than before, more efficient, but also, I mean, it's it can make mistakes, right? It can make mistakes. Why it can make mistakes? Because a human who has been dealing with these problems also, they can make mistakes. It's not making mistakes because machine learning can make mistakes. It makes mistakes because the data set which we collected, maybe it has some cases which is not wrong, which is not correct, right? Because the people who has been making those decisions, of course, they are making some mistakes, maybe 10% mistakes. And that is why people get angry. I mean, you apply for a loan, you want to buy a new car, for example, and they should say no, you cannot get. Oh, I should get a loan. So you go another bank, and from the other bank, you will get the loan. So he did a mistake, in fact, because he lost a good customer for his bank. But you know, they are, I mean, critical because maybe they try to avoid customers who will not pay back to the bank, for example. So this is a problem. But machine learning and artificial intelligence can make mistakes because the data has been collected from people who can make mistakes. I mean, artificial intelligence or machine learning, it's not intelligent. We just train it using data. And if those data are good enough, the model will be good enough. If the data is huge and it's covering different, operating regions, so it will be fine. So for example, if you look into this example, all data are maybe from 4 to 6, right? this, I mean, cluster. I mean, it's located between that place. And what if we got a customer here? What if we got a customer here, right? So maybe he will be misclassified. So if I got a customer here, for example, imagine we got a customer here. So he will be misclassified as blue, and he should be red. Do you know why? Because my model, it's a brand new data point for my model, and my model didn't see this data before, so he has no idea. I mean, we just make judgment, we make classification based on historical data, and we didn't have this case before. So this is a problem. If you want to build a machine learning, which is clever enough, you need to update the model all time. And that is why, I mean, last week we have been talking about expert system. In expert system, instead of building a system who will solve the problem in this approach, we can build a system using role-based system. So we collect the knowledge from people who are working in the bank, and we build a knowledge base, and this knowledge base will make those decisions. But once we build the system, it will not be able to tune it. You have to use it as it is, right? So so you cannot modify, you cannot fine-tune your model. But in case of machine learning, no, it can be trained all time, as you can see here. If I got a new data for iris dataset, for example, I will just upload it to my machine, and I will train my model. Do you see this one? So this one can train, this one can train, but expert system cannot train. When we build it, we have to deal with it, right? So you just need to survive with it. Okay, should we go to the, maybe I got a question? Yes, Magnus? Okay, it's about product. Yes.
No, you were just wondering about how the dot product worked out, so
Yeah.
I just put that in there.
Yeah, thank you very much, Magnus. Yeah. So should we go to the next part? So now we did this adaptive linear neuron. We have the training mode. Maybe if you have time, we have something called the batch gradient. In this batch gradient, this is the one which we did in fact in this example. So batch gradient means in each epoch, you apply all your inputs, all the 100 points in one step in vector form. So we need to use vectorization here. You apply all X values, all the target features to your model. You will calculate net as a vector, not as a single value. And you calculate the error in one step. And then you will use this error value for updating the weights. So in fact, in each epoch, we update the weights only one time. So we call it batch gradient. Batch gradient is small, it's slow, very slow, because you know, if I selected 10, if I selected number of epochs equal 10. So in fact, we will update the weights only 10 times, right? Maybe it's not enough. So we are updating your weights only 10 times, one time in each epoch. And the second approach, it's called stochastic gradient descent or online learning. In this stochastic gradient descent, we will do the same. We will define number of epochs, but we will update the weights one per example. So instead of applying X values as a vector, all X values at one time, no, we will apply it one by one. So in fact, we need to run a for loop inside this for loop, because we will do it example by example. So we will take the first example, we will calculate the error, we will use this error for updating the weights, and we will go to the next example and so on. So in fact, if I have 100 data points, so in one epoch, we will update the weights 100 times. And when you update more, your system will learn faster, right? So stochastic gradient descent, they call it online learning because we just update data point by data point, example by example. So if you are building a system and you're collecting data, for example, once you have a new example, you will just update. So it's you don't need to put a data as a batch, for example, and using this batch for training your model. You will do it example by example, and therefore they call it online learning. So we will adjust more frequent. In fact, there will be more frequent updates. So imagine that in this problem here for this example, if you selected 10 epoch, right? We have 10 epoch, and we have 100 data points. So in this case, we will update the weights. How many times? It will be 10 times 100. 10 times 100, so it will be 1,000 times. So we're updating the weights 1,000 times instead of 10. So do you see the comparison? So in batch gradient, we update the weights 1 time per epoch, but in stochastic gradient descent, we update it, it will be 100 times or n times per epoch. If the size of the data points are n, so it will be n times the number of epochs. So we will update more frequent, and when you update more frequent, you will your system will learn faster. So we call it stochastic gradient descent. What is the difference between batch gradient and stochastic gradient? In batch gradient, as you can see here, we need to store all my data points in my memory, right? Because I need to keep it in my memory, because each epoch I need to apply all those data points to my my perceptron and calculate the output and calculate the error. So in fact, we need to keep all x values. We need to keep all net values. And I need to keep all t values. And I need to keep all y values. And I need to keep all error values as a vector. Those, I mean, values, it's not a problem, but the problem it's in the data set. So imagine that you are working with, I mean, last year, for example, we had students, they have been working with Statens Vegvesen, and they have millions of images from all over Norway. I mean, in Statens Vegvesen, they have a machine or car, several cars. Those cars scan all roads in Norway. And each image, maybe it's like 20 meters. Its image covers 20 meters with some accuracy. So imagine that you have millions and millions of images, because they do this scanning maybe twice a year. So in fact, you have millions and millions of images. And the size of the image, it's too big, in fact. So imagine how much memory do you need? If you bought an expensive GPU, how much GPU memory you have? So if you will use a batch gradient, you will have a problem in the memory size, because I need to store all my data points in my memory, right? So it's really computationally expensive, because I need to keep all those images in my memory, and I need to keep all those net values. Each epoch, maybe after calculations, I can delete them to free some space, but it's energy, it's memory consuming, highly consuming memory. It needs very large memory. So this is the problem. And also, number of updates will be equal to the number of epochs. So it's slow. It's very, very slow. But the advantage here is that, do you see this curve? It's very smooth. I mean, this error curve is starting from, it should just move very smoothly, not bumpy, right? So it moves in a very smooth way to reach the, I mean, the local global minimum, for example. But it's very slow. But compared to stochastic gradient descent, though, I just need one image per time in my memory. So if you have very small memory, it's okay, because I just need to upload it one by one, just one by one, one by one, one by one. So it will be very good for my memory. And each time we update the weights for each example, so it will be faster. In fact, it will learn faster. And then when it will learn faster, I mean, you can, and also it's much better for escaping from local minima. So if you have a local minima, for example, it's aggressive, you know. So this stochastic gradient, it's more aggressive. So maybe it will help you to escape those local minima, right? And it's good for online learning, because if I got some new data, I don't need to keep data in my memory. When I got new data, I will just train my model. But if you will use batch gradient, if you got new data point, I need to add it with the batch and retrain my model, right? So I need to keep also all data points plus the new one which are coming. So it will be really very, very tough. Mini batch gradient, it's a trade-off between batch gradient and stochastic gradient. In mini batch, so for example, if the batch, if your data set consists of, imagine 10,000 images, so it will be impossible to deal with it, to handle it in my memory. So in this case, I can divide it into mini batches. Maybe each mini batch will be 1,000. So in this case, it can be handled by my memory, and I will just do like batch gradient, but in mini batches. So I will divide my data point into my data set into small batches, and I will work with it. So I will share my slides one more time with you. If you want to take break, please let me know. Okay, so we can take a break, and after the break, we will go to because we did that part. So yes. Okay, so we will start in this. I mean, making a comparison of the learning rate after 10 minutes. So we can meet again at 12, for example, 46. Hello? Hello. So now it's 48. So are you back to your computer?
Yeah.
Okay. So I will just make.
Ibrahim,
Yeah.
I was wondering about something about the exam.
Yeah.
Will the oral exam be based on 100% theory, or will it be based on a project?
No, the oral exam, it's just oral exam. Some questions in each section of for example, in machine learning, perceptron, feed-forward neural network. So you will see, for example, what is learning rate, what is gradient descent. So it's just the questions. But in the last years, we have for the exam, we have 20 minutes. And in last years, we used 5 minutes optional for anyone who want to present something as a starting point. So for example, if you have a project and you want to, present it, you can just present it in the exam, for example, and we will take maybe 5, 6 minutes, 10 minutes for presenting your project and getting some questions and answers in that project. Plus that, so for example, if you selected to have a project in expert system, so maybe we can just have the project in expert system and ask you in other sections, for example, in neural network, in optimization, and so on. So in the last years, usually we have 20 minutes for exam, or maybe 25 minutes, but it's optional for anyone to make a small presentation about a mini project, for example. So if you have been working with a project with a data set, for example, you can make a presentation and you can talk about it as a starting point, and the rest of the time will be used for questions and answers. So don't worry about the exam. I mean, exam, it's not a problem at all. I mean, the most important really is to learn something from the course and for the project. In fact, so my goal, it's not the exam. My goal, it's your bachelor project. Because in your bachelor project, many of you, I mean, in the last years, many people start working in optimization, in machine learning, expert system. So in fact, so they need the knowledge and the skills to implement their project. So don't worry about the exam, because the exam, it's an oral exam, and I don't know if you are checking grades from last years. It was very good, in fact. So the exam itself, it's like a classroom, in fact. So it's the questions and the answers, and sometimes it's not me who is asking questions. Sometimes you ask me questions. So we just, it's like a discussion about the course, if it was useful, not useful, how can we improve it in the next years. And we ask questions, and if you have some project, if you have some idea, you can present it. So so it's not like exam like traditional exams. It's a good day because we meet people in person and we discuss about the course, how can we improve it in the next years, what has been done good, what has been done bad, so we can improve it. So the exam, it's not a problem from my point of view. So don't worry about the exam at all, because for example, today we have been talking about a perceptron. What is a perceptron? How can we what is the learning rate, for example? What is the difference between different activation functions? So those are the questions which we will ask in the exam, right? So I can just ask you, you have a data set, and this data set, it's for regression. Which activation function will you use, for example? Of course, you will say, no, we cannot use step function. We need to use linear function because it's a regression problem, and so on. So it's something similar. I mean, learning rate. What if the learning rate is too high, and what if it's too low, right? What would be the difference? What will happen? You can test it now in one of those, programs, examples. If it is too high in this example in front of you, what will happen? Your system will not diverge. Maybe it will converge. It will not converge at all, right? Because it's too high. So the system overshoot. In fact, do you remember the graph for this? Do you know this graph, right? So maybe we will just oscillate here. We will overshoot across the global minimum here, and we will not converge. So yes. Okay, so in this slide in front of us, we have two learning rates. One is, 6 times 10 to the power of -3, and one is 0.0001. One is small value, and one it's little bit 6 times this one. So when it's this value, you can see the system that it converge, right? So we started from very high value, and it decreases with time until we reach 20 epochs. When it's 6 times higher, what will happen? The system will fail to converge, in fact, and it will diverge. So the error will increase because we keep oscillating, we keep overshooting, in fact, across, this local minimum or global minimum. So this is the difference between high learning rate and the low learning rate. So low learning rate, we will converge, but it will take more time, right? But when it's high, we have the risk that it might, we might oscillate, we might overshoot the global minimum and not be able to reach it at all. So you can test it from the example. Do you remember this? I know if you can run this example one more time for this function, which we, yes, this function. I don't know if we increase
Change
this.
the screen you're sharing.
Okay. So I will just share my whole screen. Okay. Do you see this example here? I don't know if we increase this one too much, what will happen? Do you see? We cannot converge. We diverge, right? Do you see this simple problem? So maybe 3.1. What will happen? We don't have any. No, I don't know. In fact, no. It's very large values, very large value. So we can select small value. So it's a problem. So when the learning rate is high, in fact, we have a big problem because we cannot converge. We will just keep oscillating across. Now we can reach. In fact, we can reach the point. But when it's too much, when it's too large, it will be a problem, and we will keep oscillating. But we need to have a good example. In fact, so the problem here, we will start from some random point, and if you cannot reach this point, you will just keep oscillating. You will jump from here to here, from one side to another side. Keep jumping from one side to another side, right? So you will not be able to converge. You will fail to converge if it's too large. So the learning rate, it's hyperparameter, and selecting this hyperparameter also, it's very critical, and we need to be careful when we're selecting it. Yes. Okay, so we will go to the next slide. It's how can we improve the gradient descent through feature scaling. Feature scaling, we collect data. So maybe those values are very high or very small, right? So imagine that for the banking example, I'm collecting data about income of people because you want to get a loan, for example. So one feature will be the income, one feature will be age, right? So one feature will be, for example, if you are getting 1 million NOK per year, so one feature will be 1 million. The other feature, it's the age. You are 25 years old, or 22, for example, or 20, or 35, or whatever. So this number, it's 1 million, and this number, it's 34 or 35, correct? So the range and the scale of features is different. So it will make a problem for my machine learning. Imagine your perceptron. We have inputs. We multiply inputs by weights. We calculate net value. We send this net value to the activation function to make decision yes and no. Now we have one feature which has a scale of millions, and the other one it's just by tenth or hundreds, for example. Or imagine it's a gender, so it will be male and female, for example. It could be 1 and 0, or +1 and a -1, right? So some values are very small, and some values are very large. So it will make a problem for my machine learning because those features are multiplied by weights. So it will impact the training process, in fact. Someone will have a huge impact, someone will not have any impact, right? Less impact. So in this case, to avoid this problem, we need to scale, we need to standardize my data sets. So it's very important to have to try to put it as a standard normal distribution. So we need to have all my variables should have a mean value of 0 and a standard deviation of 1 using this equation. So its feature we will subtract from it its the mean value and divide it by the standard deviation to standardize it. In this case, my model will be stable, and my my learning algorithm will be able to train my model more effectively, in fact. So the accuracy will improve, performance will be much better, and so on. It's important also because not only, because of the activation function, right? So, but if we go back to those activation functions, do you see? I will go back to the active. Imagine we have this activation function, right? It's a sigmoid, for example. Imagine this sigmoid function. So in fact, this sigmoid function, it converts all x values. Do you see y equal 1 divided by 1 plus exponential minus x? So in fact, this sigmoid function, it converts input values or net values from its range into 0 and 1, into a range between 0 and 1, right? So we convert those numbers between, it converts the x values or the inputs from its range. I don't know what is this range. It could be by millions, into 0 and 1. So it has this impact of squashing inputs. It squash inputs into 0 and 1, right? And if you look into this sigmoid here, small values, imagine I have a value here, it will convert it into 0.5. Some values here will be converted to 0.6, 0.7. And until we reach 1, maybe 2.5, it will be converted into 1. 2.5 and above, all those numbers will be converted into 1. So imagine that we have a model, and it's for this banking example, for example, and we have people with income, we have people with age, for example. So imagine that it's the income. So all income higher than 2.5 will be converted into 1, regardless of the amount. So the one who is getting 100,000 per year, he will be the same as the one who is getting 1 million and 10 million per year. So in this case, we squash lots of information into 1, which means we will lose lots of information, in fact. So we lose information. So this squashing impact of the activation function, it's catastrophic, in fact, because we lose information. We squash lots of knowledge, lots of information from my feature into 1. I combine all those values. So I don't care if you are getting, especially here in this sigmoid, for example, if you are getting 10 krona per year, it will be the same like getting 1 million krona per year, because 10 krona will be squashed into 1, and 1 million krona, it will be squashed into 1. 10 million NOK, it will be also squashed into 1 using this activation function. So in this case, I have a data set, and I have the income, the distribution of the income of people from 100,000 to 20 million per year, for example. All those information, we squashed it into 1. We ignored it. So it's a problem, really. If you will work with the data set as it is, it will make really big problem for us, right? It will make huge problem for us. Why? Because the model will not feel it, will not feel the variations on your data set. So if you will keep it as it is, but if you standardize it between, so it has a minimum 0 and variance 1, in this case, it will be standardized. So we will have more variations. My model will understand the variation in your data set, and it will use it for solving the problem. So we will have those, we will keep those variations. But if you didn't normalize, or if you didn't standardize your data set, we will lose all those informations. Those informations are important, because at the end, my model will ignore the income, right? Because all income, all incomes have been squashed into 1, right? So in this case, it will not have any impact, in fact, in solving my problem. I will build a machine learning which works fine, but in fact, in reality, it will not work. You will provide inputs and you will get outputs, so it works technically, in fact. But in the context of the problem which you try to solve, it will not make any difference, because it will be really a problem. So you need to standardize your data set for those activation functions. look into this hyperbolic tangent. All inputs here, because this is x and this is y of x, all inputs has been squashed from their range. I don't know the range. Maybe it's from 0 to 10 million, and from 0 to minus 10 million. All those numbers has been squashed into 1 and minus 1. And the only small portion has been converted or mapped into numbers between 0 and 1. Very small portion, right? But if you can standardize your data set, so all my data points are between minus 1 and 1, for example. So in this case, I will keep all variations here. So my model will be able to differentiate between the one who is getting 100,000 and the one who is getting 1 million. So it will make sense. I mean, the data set will make sense for my model. So standardization is very, very important. How can we do it? Very simple. Just this equation, x equal x minus mu divided by sigma. And implementing it, it's just simple. I mean, and also when we start in SQL learn, for example, we have functions which can do it, but it's one line. Do you see? It's one line. X minus x mean divided by x standard deviation of x. So x minus mean of x divided by standard deviation of x. And when I plot it, so this is the original. I mean, this one it's for x1 and x2. Maybe it's petal length and sepal length. So when we standardized it, it was in its range from maybe from 5 to 8. Now it's standardized. It has a mean of 0 and standard deviation of 1. And it's the same for the other variable. And imagine if this one was income, right? Imagine it's income, and maybe the income it's from 100,000 to 10 million per year, for example. So we need to standardize that so we can keep variations. My model will be able to capture those variations in my data set and use it for solving the problem. So it's one line, just one line. But please remember to do it. Remember to put this one line for your features. So when you are working after uploading your data, you need to standardize that. It's when I trained in fact my adaptive linear unit with the standardization, I got this training error curve. So I just I mean, you need to do it and test it. So okay, do you have any question in the last part? Do you remember the data set which we used the last time? This annual salary data set. Can you check it, please? I mean, last time I guess Rasmus he helped us. Rasmus. Can you upload this data set and try to implement a regression model? So the regression model will be y equal mx plus c. M is the slope of the line and the c y intercept. So in fact, in the regression model, we got this line, right? We got this line from the regression model. And those are the parameters of the regression model. This one is M, this one is C. We got this line. So can we do the same using adaptive linear? Can we do the same using adaptive linear unit? Can we use a perceptron for doing the same? Because we have been talking about classification. What about regression? Can we use a perceptron for regression? I mean, as I told you, in regression, we are interested in the line. But in classification, we are interested in the line which will divide my data set into two classes. So in the classification problem, we try to find a line, and all data points above the line, it will be one class. All data points below the line will be another class, right? But in here, when we are working with regression, we just need to get the line. We want the line. The line is very important because in this problem here, I mean, this axis, it's years of experience, and this axis, it's annual salary. So if I have been working at NTNU, for example, for 5 years, I need to get a curve like this one, in fact, but maybe it's a flat. So if I have been working here for 5 years, what will be my salary after 10 years? I need to know. So we need to collect historical data, maybe in the last 20, 30, 40 years, for example, build a model, and this model, from this model, we will get this regression line. So if you have been working here for 1 year, maybe this one will be your salary. It's expected if you will continue with us here for the next 8 years, you will get this salary, correct? So now I can use it for making predictions, right? If you have been working with us for 2 years, after 2 years and a half, you should get this number, for example. So it's a regression. I mean the slope of this line. So how can we characterize this line? It's y equal mx plus c. M is the slope, and the c it's a intersection with this y-axis. So we can build a regression model using a statistical approach to find the mean and the intercept, and find the line and use this line for making predictions. And it's the same for stock market, for houses market, for example. So if you bought a house this year with this price, what will be the price next 2, 3, 4 years? Right. So this one has positive slope. Positive slope, it means positive rate of a change, right? So it's positive. So the rate of a change is positive. So it will increase by positive value. If it is negative, it means the price will go down, right? If it's a flat, it means the slope equals 0, right? So if I have a line here which is horizontal, so it means this is a line with 0 slope. So there is no rate of a change. Rate of a change equals 0, which means my salary will stay the same. It's the same. If you have been working here for 2 years, for 10 years, it will be the same, no change, right? So the model, if I want to use a perceptron or adaptive linear, I will call it adaptive linear unit. So we will differentiate between adaptive linear unit and a perceptron. A perceptron, the activation function is unit step, but in adaptive linear unit, the activation function is a linear function. So I just need to build something like this one. I have one input x. X, it is the years of experience, right? Years of experience. And the y should be the prediction of annual salary. And if I have only one input, so the model will be like this one: y equal omega x plus b. Y equal omega x plus b. I need to find omega, and I need to find b. So we need to build adaptive linear unit for doing this. So you have the link for this code. Yes. Okay. Maybe I can go to So this is the one which I will share my screen with you, so you can. So I will stop this one, but just remember, because we will leave this one now to the code. So remember that your model will be y equal omega x plus b. You have only one weight value and a bias. This weight value, it will act as a slope. B will be y-intercept. And if you look into numbers here, this number we got it from the regression model. This number we got it from this adaptive linear unit. Right? There are some difference because I didn't check accuracy, which one is more accurate. Right? We can train this one more. I don't know. So, but I will just share, stop sharing this one and share my code. Okay, do you see? This is the code, and it's called adaptive linear unit for regression. We will run this part. Now we have the file, the salary data set. Do you remember it? So I will run that part. I need to upload my data points, salary data. Now it has been uploaded. Now I want to extract my feature and my target feature. So X will be my feature, input features. So X it's years of experience, right? X it's years of experience. and Y it's the annual salary. So I will run it. So we have this curve. So this is the historical data which we will use for building the model. As I told you, if you are doing it, for example, for NTNU or for some companies, for example, in Olusund, I will collect those data, historical data from Olusund, for example, and I will have a regression model. And if I want, for example, to attract investors to Olusund, for example, I can say, okay, no, we have positive exchange. We have positive rate of exchange. So if you will invest 1 million here, I mean, after 3-4 years, this million should be 4-5 million, right? So, I mean, when you talk to people, you need to find, build models which can convince them, and you can convince them by history, by historical data. So now this is my data points. So we have this graph. It's years of experience. It's annual salary against years of experience. Now I have the model. It's the model which we did last time. No change at all. At all. It's the same. So this is the one which we used last time. No change at all. Now I will scale my features. Do you remember? I told you this is very important. It's not scaled features or standardization. So it will be x minus x mean divided by x standard deviation. So we call it standardization. Right? So we will do it. Now we got our model, right? So we got the same regression line. We got this regression line. Maybe you can play with it. Maybe increase this learning rate and try to train it another time. I mean, it will be okay. I mean, maybe we can decrease, maybe we just say, okay, it's enough to have 100 epoch. So you will get some solution like this one. So finally, we have a regression line. So in fact, instead of working with a statistical approach, because the regression model, if you want to build a regression model, you need the statistical approaches. And it's a problem because when you build a system, you have to use it as it is using statistical approach. But if you will build your system using adaptive linear unit, what will happen? If I got any new data point at any point in the future, I will retrain my model, right? So in fact, when you build a model, when you have this model, we have the weight value and the bias. Do you see? This is the bias. This is the bias value, and this is the weight, correct? So in fact, this is my model. So at the end, y equal this number multiplied by x plus this number. This is my model. So at the end, when you build a model for a bank, for example, you don't need to give them your code. In fact, you just need to give them those two numbers. This is my model. So in the future, in fact, if you got new data point, if you got some Excel sheet and discovered an Excel sheet in somewhere, and you need to retrain the model, we can retrain the model. Just upload it to your Python and retrain the model. So those numbers will change a little bit. So your model will be smarter. But in case of statistical approaches, I need to keep all historical data, right? So if I build this my regression model using a statistical approach, and I got a data point in the future, what will happen? I need to keep all historical data. I cannot give up my data because I need to keep it with me. Because if I need to update my model in the future, I need to use the data which I used before plus the new data. It should be one block. But in case of perceptron or adaptive linear unit, no, I don't care. So just ignore those data, clean your memories. I don't need those data, and my model will be like this one. And if I got a new one example in the future, I will use this example to just update my weights. I will just use this single example for updating my weights. So we will not lose the knowledge. But in case of regression model, you build a regression model, and for some reason the hard drive was destroyed. You don't have historical data, so I cannot retrain my model without those historical data, because I will get different numbers. I mean, for a statistical approach, I need huge data set. In fact, to get more accurate model, I need too much data, and I need to keep all those data in my computer, for example, just in case in the future you want to update your model. So I need to use all those historical data. But in case of our adaptive linear unit, neuron, for example, no, I don't need. I just train it. And once we have those numbers, it's fine. I will just clean my memory. I don't need those data points at all. But in the future, if I got one data point from Oslo, I will retrain my model using this one. But remember, when you retrain, you cannot start from. You need to disable this part, this line. Correct? Do you see this one? So when we train the model, so I need to write a function for retraining, right? And in retraining, I should not initialize the weights by random values. No, I don't need, because I have already it's already initialized with those values. I need to initialize it with those values. Because if you will initialize it by random values, you will start from scratch, and we don't want to start from scratch. Right? So I will just run this one for the single data point which we got. So in this case, my model can train every day, for example. So I'm using a model. This model will be used by a bank or by a company, and they collected some data points after 2-3 weeks, for example. Okay, once we have some data points, I can just update my model. So when we update my model, please disable this one. So I will put it here. Disable in retraining. If you retrain your model, you need to disable this line. Because we initialize our weights if we will train the model from scratch. But if you want to retrain it with some few data points which you got lately, in this case, you need to disable this line, because I don't want to start again from random values, right? I need to keep those values and just updating my weights using the new examples which we got. In addition, also in a statistical approach, it's very sensitive to outliers. So we have here an outlier. So it's a problem, in fact, because this regression line will impact a lot by this outlier. And if you got an outlier here, it will be a problem. Maybe it's not the case in adaptive linear unit, or it's not sensitive to outliers. So using machine learning or using a neural network with Okay, so do you have any question for this part? So this is the, this one, it's the regression model, and we have also the regression model in the same file. So in the same file, you have the regression model, and you have the adaptive linear unit in this file. So you can go to it and try to spend the time with it, and just to try to upload a new data set and try to play with a new data set. Yes. Any question, please? Do you have any question? I mean this one, it's just a comparison between the impact of the learning rate, for example, for the same model. So I have adaptive linear unit, and I trained it with small learning rate and high learning rate. What will happen? No, when it's small, it will take more number of iterations to learn. So it takes here 5,000. But when it's higher, much higher, it takes less time. Right? It takes less time. It takes 50 epoch to train to give me the same accuracy. So the learning rate will impact the learning time of your model, your model. So when it's too slow, when it's too small, it will be too slow. It will take too much time to reach the same level, and then when it's too high, it will be more faster, in fact. But remember, if this one is too high, really, maybe you can diverge, or you can fail to converge. Yeah. Any question, please? So the second part, it's activation functions. So in this part, I will just make comparisons between different activation functions. So the activation functions, we can divide them into two types, linear activation functions and the non-linear activation functions. I will leave you to check this part. So I want you to read the slides from maybe 22 into 23 softmax, 25, 26. Okay. So please, from 22 to 27, I will give you maybe 20 minutes to go through those few slides, and also to go to the code, which is because I implemented it, in fact, in this one, activation functions. Can you open this file, please? Okay, I will share the link in the chat so you can open it. So this is the code, which it's a simple one. It's just implementing each activation function and its derivative. So we will go back to 22. Yes. So please, you have the code. I will give you 20 minutes, for example, to go through those few slides and check the code. Can you open your mic, please, and you can just give me any feedback?
I got a question about the exam.
Yes.
It's an oral exam, but is it possible to take it digitally? Or
Yes,
do you
it
have
will.
to be in person?
No, I guess it will be digitally. So we can do it by Skype for Business, for example, or by Zoom.
Sure.
Yeah, yeah. And if we also, it's 1-by-1, so there is no risk. In fact, if we can have it also in the school here. So
Yeah, it's a bit far to travel to Ålesund for that.
Oh, you are not in Ålesund?
No, I'm in Trondheim.
So no problem. It's okay. So
Okay.
yeah. We will manage. I mean, it's not a problem for the exam. We will manage to. If we do teaching digitally, I mean, the exam also should be digitally. It should be fine. Any other questions? So is it okay to have 20 minutes? Just I want you to go through those slides from 22 until 27 or 28, and also the code. I have also the code here. So, and I shared the link with you. So the code also, it's a simple one, right? Do you see? Just for, I do it for unit step. We do it again for sigmoid. We do it for softmax, hyperbolic tangent, rectified linear unit. So I just implementing those, just implementing the function and its first derivative. Why its first derivative? Because we use gradient descent, and the gradient descent we need to use the first derivative as the gradient to calculate the gradient. So please, can you go through it and first, and we can meet again after maybe 20 minutes. Is it okay?
Yeah, it's okay.
Okay, it's fine. So we will meet again after 20 minutes. So just please go through those slides, and you have the link for the code, and we will meet again after 20 minutes when you read it first, so we can discuss. So should we start again? I mean, we will start here from unit step. So unit step, how it look like? It look like it's used for binary classification, and it squashes inputs also into just zero, maybe zero value and +1 value. And this is the first derivative of this function. So the first derivative of step function, it's yeah, just a minute, please. We will start. I will start by quickly going through those activation functions. So we have this step function, and the step function, we use it for binary classification. And the derivative of this function, it's impulse function or delta function. And this delta function, it will be 0 everywhere except at 0, it will be 1. If it is hard limb function, and if it is symmetric, it will be 2. So this function, we can use this function for classification. We cannot use this one for regression. The second one, it's a sigmoid, and the sigmoid, it's used as a squashing function that limits the output to a range between 0 and 1. So as you can see here in the red line, this is the function. And if you can see here, this is the range of x. So it squashes all input values into a range between 0 and 1. So it has this squashing impact or squashing effect. And therefore, it's very, very important to normalize your data before training your model, normalize and standardize before working with your model. So it predicts the probability of a binary classification problem. So in the same case, we can use it for binary classification problem, but instead of classifying it into one of the two classes, it will give us the probability that this data point belongs to this class. So for example, it could be 0.6 in one class and 0.4 in the other one, which means it belongs to the class 1, for example. So this one will give us probability instead of, I mean, if we will use the binary class, if we will use the step function, the output will be just 1 and 0 or 1 and then -1. So it will decide directly in which cluster or in which class this data point belongs to. But if we will use this sigmoid function, it will give us probability. It will predict the probability. So the function, it's 1 divided by 1 plus exponential minus x, and its first derivative, it will be the function multiplied by 1 minus the function. So the green one, in fact, it will be the first derivative. This one, it's very important because we have something in machine learning. We call it vanishing gradient, and this vanishing gradient, it's when we update the weights, we use the gradient. And if you can see the function itself, the activation function, the output will be between 0 and 1, but its first derivative or the gradient, it will be a number between 0 and 0.2, for example. And when we repeat this one, when we try to update the weights in for 2, 3 hidden layers, for example, we will have lots of multiplications of this green one. So multiplying a small value by multiplying a small value, it will be a smaller value, and so on. So at some point, the gradient, the value of the gradient will be very, very small, and it will not be able to help us to train a model to adjust weights. So this is very important to plot the function and to plot its first derivative. The next activation function, it's softmax. And softmax, we cannot plot it. It's called the normalized exponential function, in fact. Normalized exponential function. It will give us the probability of an event compared to, or normalized, in fact. So the output will be the probability of an event divided by the all other probabilities, right? So it will give us a number between 0 and 1, and the sum of the probabilities will be equal to 1, right? So it will give also, so for example, if we have this problem for iris dataset, we have 2 classes. So maybe one will be 0.7, the other one will be 0.3, one will be 0.8, the other one will be 0.2. So it will give us the probability, and we can put a threshold, for example, to convert those probability into a label. So we can just say that if this, we can round it to the nearest integer, for example, right? We can so it can be converted into 1 and 0 integer values. So this one is very, very important. The softmax function used for multi-classification model, and it returns the probabilities of each class, and the target class will have the high probability. Softmax is multivariable function. Generally, you would not take a softmax of a single. You cannot take a softmax of a single variable, but we take it of number of events. So, for example, in this example here, we did the softmax. So it's exponential divided by summation of exponential, right? So when you want to implement it, in fact, it's simple. It's exponential divided by sum of exponential. And if you have some events, for example, I have some events 2, 3, 5, and 6. You take the softmax of x vector. So the output will be this one, probability, and the summation of all those probabilities, it will be 1. This one, it's hyperbolic tangent function. Hyperbolic tangent function. So the range, instead of, I mean, in the sigmoid, it was between 0 and 1. In hyperbolic tangent, it's between -1 and 1, right? So the function will be exponential x minus exponential minus x divided by the summation of ax plus e minus x. And its first derivative, it will be 1 minus tan h squared. So the red one, it's a function, and the green one, it's first derivative. And if you can compare between hyperbolic tangent and sigmoid, you can see that the gradient here, the range of the gradient is between 0 and 1, which means it's much better. So when we use it for training, the performance will be much better compared to sigmoid, because the sigmoid look into the green line. So the range will be between 0 and maybe 0.22, but in case of hyperbolic tangent, the range will be between 0 and 1. So should expect that this one will perform much better in case of vanishing gradient. Rectified linear unit. Rectified linear unit. It's activation function which used a lot at the moment, because it is used in deep learning. It is used in convolutional neural network and recurrent neural network. And the range, it's from 0 to infinity, in fact. So the blue one, it's a function. So the blue one is a rectified linear unit. And the green one, it's an approximation of this function. It's in fact an approximation. This approximation, they call it soft plus. So we have rectified linear unit and soft plus. So it's because when you differentiate this rectified linear unit, it will be step function, right? 0 will be 0. This one x. So when you differentiate x, you will get 1. In fact, so it will be like a step function. So the differentiation first, the derivative of rectified linear unit, it will be in fact square. It will be step function. But the softmax, when you differentiate it, you will get something like sigmoid. You will get like something like sigmoid. And soft plus, of course, it's a smooth application approximation of the rectifier. So it will be like this one. Do you see? So the red one here, it's rectified linear unit. The blue one, it's the first derivative of it, which will be like a unit step. And the red one here, it's softmax. And the softmax, it's approximation of rectified linear unit. And when you want to get its first derivative, it will be sigmoid, right? So imagine that your gradient is calculated by a sigmoid. So it will perform much better than using a sigmoid as an activation function, because the range of the first derivative now, it will be a number between 0 and 1. So it will perform much better with vanishing gradient problem. You have the code. You can just go through the code, and if you have any question, please just open your mic and ask me. I mean, we go through those activation functions because those activation functions are important. It will give you impression about the importance, how it is important to normalize or to standardize my data set. Very important. Why it's important? Because of the activation function. So I will just share my slide because you have the code already. So to make it more clear. So when we study those activation function, we know that, okay, so do you see if you are using hyperbolic tangent? So hyperbolic tangent, it squashes all input from its x values, right, into a number between -1 and 1. So if again, for this income problem, if you have someone who has income, imagine it's 2.5 million and 10 million, both will have the same effect, no difference between 10 million and 2.5 million, because those two numbers will be squashed into 1. So in this case, in fact, we lose information. So all customers, if I'm building a model for bankruptcy, for example, and we are talking about companies, how much assets they have, how much resources they have. So maybe it's like, so the company which is located here, it is the same like the company which is located here. So if someone has a startup company here, and the value of the company is 2.5 million, it will be like a company which worth 10 million or 10 billion, for example. So of course, this is not correct, because now we are squashing the information, we are losing knowledge, we are losing information from my data points, and it's important to keep this knowledge. To keep this knowledge, you need to normalize all your data points or standardize your data points. When you do it, you will get much better performance in your model. Your model will learn faster. Why it will learn faster? It will learn faster because now I have rich data set. I have a data set which has lots of knowledge. But if you didn't normalize or if you didn't standardize, your model will take much more time to train. Maybe it will converge, maybe it will not. Maybe it will not. I mean, I don't know the performance. We need to test the performance to see if these numbers are correct. So we need to test it with a domain expert. But when you normalize, we will be sure that all data points will be located in this place. Do you see? So I will keep variations. I will keep the variability which we have in the data set. So in this case, my data set will be more, it will have rich information, and those information will be used for solving the problem. So it's very important to normalize. Don't go for any problem without normalizing your data. At the beginning, just plot your data to visualize it, how it looks like. Try to generate a table from your data, minimum, maximum, standard deviation, so you can know something about variation of your data set, how it look like, and do normalization, do standardization before training your model, because the performance will be much better. You will have a model which is more robust, in fact. So please, do you have any questions? One last comment about the rectified linear unit. So the rectified linear unit, they are using it today in deep learning, for example, because of this one. You see, because its first derivative would be a unit step. So when it's a unit step, it means the gradient will be a number between 0 and 1. But if you will go for this sigmoid function, for example, no, it's a problem because the output would be the gradient would be a number between 0 and 0.2. And when we multiply very, very small numbers, we will get much, much smaller numbers. 0.2 times 0.2, it will be much, much smaller numbers. But when it's 0 to 1, so we will keep the gradient, and it will help us to update our weights. Why? Because delta omega, remember all time, delta omega equal minus eta multiplied by partial e by partial omega. If this partial e by partial omega, it's very, very small, what will happen? Maybe delta omega will be very small. And when it's close to 0, what will happen? We will not update the weights. So in fact, in training, we go forward for calculating the predictions. We calculate the predictions, and we go backward, calculate the error, and we will calculate the gradient and go layer by layer, updating the weights. Maybe in the last hidden layer, it will be okay because the gradient will be larger. But when we propagate to the layers in the front, what will happen? This value will be very, very, very small, in fact. And when it's very, very small, maybe delta omega will be a number close to 0. And when it's close to 0, we will not update the weights. So you will initialize it with random values at the beginning, and you will not be able to update the weights because delta omega is very, very small. Yes. Please, can you open your mic and just discuss with me if you have any questions?
Rectified linear unit. Won't you have a problem with if you have the value exactly 0 because the derivative doesn't exist at that point?
Yes, this value. Yes, correct. And therefore they use soft plus. They used this one as an approximation, in fact. So this one, it's smooth, and we don't have this abrupt change, right? So in fact, in reality, they use soft plus as an approximation of the rectified linear unit.
So if the soft plus used in neural networks instead of the rectified linear unit?
The soft plus?
Yeah.
Yeah, it's approximation. It's the same. It's just avoiding having this sharp. Do you see the output also will be a number between 0 and 1? So instead of having a step function, it will be sigmoid function. So the first derivative will be sigmoid function. So you will have this smooth transition between 0 and 1. So you will get all numbers between 0 and 1. You will have a range. It will be float number. But in case of ReLU, it will be just 0 and 1, correct? So it will be zeros or ones. But in case of soft plus, you will have all range between 0 and 1. So the soft plus, I mean, usually they use it as an approximation of ReLU because of this point, which you mentioned. But I mean, if we will study deep learning, I mean, we need to check maybe the performance of ReLU and soft plus. Is there any difference? Because I mean, the value at 0, it's not a problem, in fact, because you can just say when x is greater than or equal, I mean, it should be fine. And in implementation, technically, it should be okay. But usually people prefer to use soft plus as a replacement or as an approximation of ReLU. Any questions, please? I want to be sure that people are maybe watching or so please, can you say something? Okay, thank you very much. Thanks, Arland. So at some point we need to start working in our project, in fact. So So I wish at some point that we can start. I mean, maybe each one can find a data set, for example, and can start developing his. I mean, solve his own problem. And I wish if we can have one day, for example, or 1 week, for example, where people can present their solution. So if you will work in the home assignment individually or in groups, for example, you can pick a data set, maybe from Kaggle, for example, or from anywhere. You can start working, and we can have one day for people to present their solutions. As a startup, now we have those models, but next week we will be working with some libraries to make it easy for us, so we can import some models and play with it. So we will see. Okay, so now why differentiation and the derivative? We know it now because we need it because of gradient descent, right? So if you have this function, it's similar to the function which we implemented this morning, y equal x squared minus 2x minus 3, for example. And we will initialize, we need to find x which will minimize this function, right? So we will start by random at some point, maybe in this side or in this side. We need to calculate the gradient. So we will get the first derivative. So it will be 2x minus 2. We will substitute x by this x value which we selected. We will find the slope. I mean, this value, it will be the slope of the tangent, right? If it is negative, it means we are moving in this direction. If it is positive, it means we will be here. If you want to find the equation of this line, if you want to plot this line, in fact, this tangent, you need to find y. So substitute by x into this equation to find y. So now we have 2 points. So in this case, we can find the equation of the tangent. And for updating x value, so delta x will be minus eta multiplied by dy by dx. So dy by dx, it will be 2x minus 2 multiplied by negative eta. So just multiply. If x equals 0, for example, what will happen? No, sorry. I guess this one is not correct, right? Why this one is equal? X equal minus 1. So when x equal minus 1, so it will be minus 2 minus 2. It will be minus 4 times eta. So it will be 4 eta. So x equal x plus delta x. So it will be x plus 4 times learning rate. If you select learning rate 0.1, for example, so in this case, the new x value will be minus 0.6. So if you selected minus 1 as a starting point, so the next value will be minus 0.6. So in this case, we are reaching. We try to be closer. We try to move toward the global minimum of our function. We have this table, and this table, it has lots of activation functions. So we have this linear function, fx equal x. So the first derivative, it will be just 1, right? Binary function, it's a step function. So this is the first derivative, right? This is logistic or sigmoid function. So it will be like this. Hyperbolic tangent. So we have all those functions. So we have many different activation function, and the activation function, in fact, it's hyperparameter. So we need to select. How can I select a function? It's hyperparameter. So no one knows. I mean, you need to check it by yourself. Maybe you need to plot your data to understand your problem. You need to decide which function will fit my model. If it is regression, for example, so in this case, I need to use linear function. If it is binary classification, I can just use this one. If I'm interested in the probability, maybe I can use a sigmoid or logistic function, and so on. If it is, if I have vanishing gradient and deep learning, so in this case, I need to use a rectified linear unit, or parametric rectified linear unit, or exponential linear unit, soft plus unit function, and so on. So which activation function will fit your problem? You need to do it by yourself. You need to check your problem. You need to check your data set. You need to, by trial and error, If this one is not working, you need to try something else, right? So it's hyperparameter. Hyperparameter, which means we need to find a way to do it, right? Yeah. Derivatives of activation function, it's all the derivatives at the same place. So the blue one here, I'm interested in the green one. So the green one, it's sigmoid. The blue one, it's sigmoid. Both are very bad, in fact, in vanishing gradient problem. Both are very bad. Which one is better? Maybe this one. This one is okay. So this one. So in fact, this one, it's soft plus. It's the first derivative of the soft plus, because the output will be a number between 0 and 1, or it could be a unit step. This one, we got it by differentiating ReLU. So those two ones are modern. They are using it in deep learning because it resists this. It tried to overcome the problem of vanishing gradient. Yes. Okay. So ReLU and vanishing, I just mentioned that already, but it's a graph where we have the sigmoid and ReLU in one graph, just to see the difference. So the sigmoid, it squashes all inputs. Do you see? We have this problem. So the inputs, it's from -10 to 10, and it could be from -10 million to 10 million. We don't care about the number because all those numbers will be squashed into 0 and 1. Do you see? All those input values will be squashed into 0 and 1. So if you will play with sigmoid without normalization, without standardization, you will be under high risk, in fact. Risk of losing lots of variations in your data set, lots of knowledge, because all those values will be squashed into 0 and 1. So my income is, imagine, my income is 1 million per year. Your income is 20 million. Both of us will be in the same category. If you didn't normalize, if you will be if you will normalize, maybe I will be here, you will be here. So now we will keep the variations of the data set. We will keep the knowledge from the data set if you will normalize. So normalizing, it's important because we will keep the variations of my data set. My data set will be rich, in fact. It will have lots of variations, lots of knowledge. But if you will use it as it is, we will show out some knowledge. We will ignore some knowledge, which might be important for my problem. In case of ReLU, we don't need, in fact, to normalize. Do you see? Because in ReLU, all negative values will be squashed into 0, which is a problem, in fact. So this one also, it's a problem in ReLU. All negative values will be squashed into 0, but all positive values will stay as it is. So 5 will be 5, 10 will be 10, 10 million will be 10 million. But -1, it will be 0. -10 million, it will be 0. So in this case, maybe we don't need to normalize because this rectified linear unit, it can deal with numbers as it is. So the function is simple. It's just max of 0 and x. So all x values will remain, all positive values will remain as it is, and all negative values will be converted into 0. And the first derivative of this function, it's the black one. Do you see? No, it's not the black one. In fact, it's a derivative of the soft plus. So the derivative will be like a sigmoid, but this sigmoid, its derivative will be this small one. So the performance of the ReLU or soft plus is much better for solving the vanishing gradient problem, and therefore it's used now in deep learning. So in deep learning, in fact, we can work with raw data, right? So just build a model, and this model will just work with the raw data. We don't care about normalization, standardization, because of the activation function which we are using here. Because we are using ReLU or soft plus or any one of those functions in this table. Do you know? So for example, if ReLU has a problem with negative values, you can just use parametric rectified linear unit. You can use exponential linear unit, right? You can use soft plus, it's the same problem also, but it's good for part from the negative values, because some of the negative values will be converted into some small positive value, and the rest will be converted into 0. So the selection of the activation function, it's based on the knowledge, in fact, domain knowledge. You need to plot your data points, you need to understand how it look like, and you need to decide which function we will use. Right? Because if in deep learning, for example, if you selected rectified linear unit and you have too much negative values, you have, I mean, lots of negative. If it is image, it's okay because image pixel values, it's just positive values, right? But imagine that you are working with data sets which has lots of negative values. All those negative values will be discarded or ignored, right? Because all those negative values will be squashed into 0. So in this case, I cannot use rectified linear unit, and maybe it's much better to use parametric rectified linear unit or exponential linear unit, or at least a soft plus, because when you look into the part here, some of the negative values will be transferred into a number close to 0, but not 0 in fact. Yes. So I'm just explaining here this vanishing gradient problem. So in vanishing gradient problem is encountered when training artificial neural network with gradient-based learning methods and backpropagation. We know now why we have this vanishing gradient problem. It describes a situation where a deep multi-layer feed-forward neural network or recurrent neural network is unable to propagate useful gradient information. We don't have any useful gradient information. It's almost 0 from the output end of the model back to the layers near to the input. And hence, inability of the model with many layers to learn on a given data set or to prematurely converge to a poor solution. So I have a model, and imagine why we didn't have deep learning before. You have a model. If you select two deep learning, two hidden layers, maybe it's okay, right? But if you selected 5, what will be the situation? Maybe we will be able to update the weights of maybe the 5th, 4th, 3rd, but the 2nd and 1st we will not be able, because we will not be able to propagate any useful information to those layers close to the input of the model. So if we initialize it with random values, maybe we will keep those random values all time, which might be a big problem for us. So in gradient-based learning, each of the neural network weights receive an update proportional to the partial derivative of the error with respect to the current weight in each iteration. So we have this equation all time. We need to put this one in front of us. Delta omega equal minus eta multiplied by the first derivative of the error with respect to this weight value. If this value is small, what will happen? If partial E by partial omega is very, very small value, what will happen? Delta omega will be also very small or close to 0. When it's 0, what will happen? We will not be able to update those weights. So we need to select an activation function which will maximize this one, partial E by partial omega, because this is the signal, or this is the values which will be used for updating weights. If these values are very, very small, what will happen? Omega equal omega plus 0 all time. So we will keep initial values, random initial values. So in some cases, the gradient will be vanishingly small, effectively preventing the weights from changing its values. When it's very small, we will prevent the weights from updating its values. And in the worst case, the training will stop. Correct? Some layers, at least some layers, will not train at all, right? So in this case, we don't need to go deeply. If you will be so now if you are developing an application in shallow learning, please don't go so much deeply, because you will have this vanishing gradient problem. And try it. Just try it. Go for shallow learning, not deep learning, and select, for example, 5, 6 hidden layers, and try to see what will happen. Try to print the weights of each hidden layer after some number of epochs. Some of those weights, or you can plot it, for example. Some of those will change. Some of those will stay as they are, in fact, because they are not receiving any useful gradient information. Because the partial E by partial omega, it's very, very small or close to 0. ReLU is used to improve the flow of gradient through the model. ReLU is much better, because the first derivative of ReLU, it will be this step function. So it will help us to improve the flow of gradient through the model. So all layers will be able to learn. I talk about learning modes, and in the learning modes, I mentioned that we have 3 learning modes. The first one, it's batch gradient, and in this batch gradient, we minimize the cost function by taking a step in the opposite direction of the cost gradient from the whole training set. We deal with the whole training set. We had an example, right? And in this example, in each epoch, we calculate the error from the whole data set, right? And after that, we use this error for updating the weights. So we update the weights one time each epoch using the error from the whole, or the gradient from the whole training set. Batch gradient, it's okay, but it's a problem for my memory because we need to keep all my data points in my memory, because each time we need to do those calculations in each epoch, and it's computationally expensive because we do lots of calculations. In fact, we do those calculations each epoch for all data points, and after that we take the gradient from the whole data set and use it for updating the weights one time each epoch. It's slow because we update only one time per epoch, right? So it's very, very slow, but also the learning, the error curve, it is more smooth, right? So I guess this is all about batch gradient. In a stochastic gradient descent, it's iterative or online gradient descent, online learning, iterative or online learning. So instead of updating the weights based on the sum of the accumulated errors over all samples, we update the weights incrementally for each training sample. So for each, we will update the weights one time for each training sample in each epoch. So number of updates will be the number of training samples multiplied by the number of epochs. So in fact here, the model will reach convergence much faster because of the more frequent updates. And the gradient here, it's based on a single training example, and therefore the error surface is noisier and it can escape shallow local minima. So it will be more aggressive, in fact, because and the error surface will be more bumpy, right? It will not be very smooth, but it will be more bumpy. To obtain good results in SGD, in fact, it's important to shuffle the training set for each epoch to prevent cycles. So each epoch, we need to shuffle your data set to just avoid cycles and repetitions. And the learning rate also, we just replace it by adaptive learning rate. In adaptive learning rate, it will be constant value divided by number of iterations. So when the number of iterations is 1 at the beginning, so the learning rate will be constant value, big constant value. When the number of iterations it's 100, for example, it will be C divided by 100. So which means we start in each cycle, in each epoch, we start with a large, in the training, in the first epoch, we start by large value, and when we are close to the local minimum or global minimum, we have very small learning rate. So we are sure that we are not oscillating or overshooting the local minimum. Mini batch, it's just it's a trade-off between the two approaches. And in this case, if your memory has a problem because maybe your data set is very large and your memory cannot handle it, so in this case we will divide it into small batches. Maybe the batch size will be 32 samples or 64 samples, 128 samples. It's up to the memory, how much how much data point you can handle in your memory at once. And in this case, we will work batch by batch, right? And we will do this batch gradient descent, but on those batches. It will reach faster because of the more frequent weight updates. So for example, imagine that I have a data point which consists of 100 points or 1,000 data points, for example, and I will divide them into 10 batches. So in this case, how many updates we will have? It will be 10 batches multiplied by number of epochs, number of batches multiplied by the number of epochs. Correct? So if it is in batch gradient, if you will run your program for 10 epoch, you will update your weights 10 times. But if you run it as a mini batch learning, and if you run it for 10 epoch, and the batch size will be 100, you have 100 mini batches. So in this case, it will be 10 times 10. So it will be 100 times. So in this case, we should expect that it will converge much faster compared to batch gradient. You have this batch gradient is applied in this example in GitHub. It's adaptive linear unit version 2. I want you, in fact, it has batch gradient and it has stochastic gradient descent. But I want you to implement mini batch gradient and you compare results. So it will be your home assignment. But I can share. I can show you this code first. So we will open it. So I will run it with you to show you the difference between batch gradient and stochastic gradient. So you have this file, and this file is called adaptive linear unit BGD versus SGD. But please, I want you, from now until next week, to try to implement mini batch gradient. For the same example, it's Iris dataset, and also we uploaded. We have 4 features. We have 3 clusters, 3 classes. We used as the first 100 points, right? As for binary classification, we use the feature scaling. So I have X, in fact, so I just did feature scaling. So X minus X mean divided by X dot standard deviation. So we can run it one by one. Uploading my data. Extracting my features. Running my cluster. So my class here, do you see my class? I just did batch gradient. This is the last one which we did. If mode is batch gradient, so I need to select the mode here. So it's learning mode or training mode. If it is batch gradient, it will be like this one. So we will deal with the net as a vector, y as a vector, error as a vector. If you will deal with it as a stochastic gradient descent, in this case, I need to have another for loop here. This for loop will help me to go through the data point one by one. So in this case, this one will be scalar value. I will take the first example. So instead of working with X, it will be XJ. So here I'm working example by example, calculating the net value, calculating Y value, calculating the error, and updating the weights, and repeating this process until you finish your training data set. So in each epoch, in fact, if you look into here, in batch gradient, we update the weights one time for each epoch. Here, in stochastic gradient descent, we update the weights, for the length of X, for the number of the data points. If this number is n, so it will be n times number of epochs. It will be 10n, right? So of course, this one should converge faster than batch gradient. So in fact, I wish if you can add here one part for mini batch gradient. So I wish if you can add a part here for mini batch gradient. This is the one which we are missing here. So we will run this one. So now I will try stochastic gradient here. Do you see? I will try SGD. So do you see? We use the 10 epoch. We use the 10 epochs, and the learning rate it's 0.1. We converge very fast, very quick. Do you know why? Because in each epoch we update the weights 100 times, right? So it's here from epoch number 1 until epoch number 2. It's only one epoch. In this one epoch, we updated the weights 100 times. And from this one to this one, 100 times. From this one to this one, 100 times. 100 times, 100 times. So in fact, it's 10 times 100, which means we updated the weights here 1,000 times. So it will converge very quickly, very quickly. We need also to add time, in fact, but it will converge very quickly. We can plot the model. So this is nice model. So we have the decision line, we have 2 classes. Now we will change it to batch gradient. We will change it into batch gradient. We will run it. Oh no, it diverged. In fact, it diverged. So we need to select a smaller learning rate. Okay, smaller learning rate. Now it's okay. Do you see? It's 20. So we run it for 10 epoch, and the error is 20, which means it needs more iterations. In fact, we need more iterations. We will change it to 20 epochs. We will run it. Look, still not 0. So we will make it 200, right? We will make it 200 and run it. Okay, now it's a closer, but I don't know in fact if this one 0 or not 0. Maybe you can plot this one here. We still have, do you see the model? We have one point located on the line, and the decision line, in fact, it's not good because it's, maybe we need to train it for more time. Okay, 500 times, because the weights will be updated here 500 times, right? The weights will be updated here 500 times. We will do it like this. We will plot this one. Okay, I mean the accuracy, it's bad. We have some. Maybe we need to make this one much bigger. No, diverge. But as you can see here in this example, when it's batch gradient, it's a problem. I need also, if you can, calculate how much memory we use. In fact, I don't know. I wish to measure, how can we measure the RAM, and so I don't know. We need to check. So if someone of you can help me, in fact, it would be great, because those numbers are very important. We need to know how many kilobytes we are using, how much running time. We need to get the running time for batch gradient and the stochastic gradient, for example, to make good comparison between the two approaches. Yes, so if I will go back to my slides, because yes, I will just show you the last slide. So it's comparison between batch gradient and stochastic gradient. In batch gradient, it's a smooth error surface. It requires more epochs because we need more time. In fact, do you see? We need more time because it's not converging here at 10. We need more time. Computationally expensive. And as you can see, this is the performance. So this is the model which we got. But if you will use a stochastic gradient descent, it's a noisy error surface. It's bumpy, which is good because it can help you to escape from some local minima. Fast to converge, it will converge much faster, and it's suitable for online learning. Because if I got a new data point, first of all, I don't need to keep all data points, because keeping those historical data, it's a problem. So if you are working with a bank, for example, if you are working with a hospital, maybe they will not allow you to store those data points in your computer. So imagine you are working for a bank, and you just need, okay, I'm building a model which will predict if a customer will leave the bank, for example, and they move to another bank, shift a bank. And you just told them, okay, I want to keep all those data in my computer because we are using batch gradient. No, I will put it on a server. They will not allow you because of GDPR, and it's a privacy of people and important, maybe transactions, because from those transactions you can know a lot about people, in fact, right? So so they will not allow you to store those data points in or data sets in your computer or in a server. So if you can build a system which you can work with online learning, I guess it will be much better. Yes. So today we are at the end of today. I hope it was good material today. You have the code, you have the slides. Please try to develop, your skills. Try to work with some other data points or other data sets, and share it with me, please. And you know, we have to today, maybe if we can say that what kind of homework we should do today, for example. So first of all, we need to plot the decision line in maybe 3-dimensional space. Do you remember when we used the 4, for example? So if you can plot the decision line, decision plane, for example, decision plane in 3D, for example, it would be great. Make comparison between. We need to implement mini patch gradient, mini patch gradient descent, right? You need to implement it. Make comparison between batch gradient descent, mini batch gradient descent, and stochastic gradient descent in terms of. We need to make comparison. We need running time, maybe, right? So running time, memory use. I don't know. I mean, we need to find accuracy, not a computational cost, right? So we need to know how can we do this. So we should have a table. So if you can put it in a table, it will be great. So we need to have a table. So it could be something like this one. We have here patch gradient descent. We have here mini patch gradient. And I mean, maybe a time, memory, I mean, performance or model accuracy, and so on. So please try to do something like this one until next week, and share your solution with me. And if you have any questions, just contact me anytime, or just we can discuss it next. Can write notes for next week, for example. So please just open your mic and give me any feedback if you have any feedback for me, just to be sure that people are watching. And any comment, anything which we need to do next time. So please, if you have any feedback for next time, just inform me so we can fine tune our performance also. So if you prefer to focus on something more, or we need to pass something, you can just open your mic, please, and just talk. Yes, it's not a homework. I can put it in Blackboard. It's fine, but also you can take a screenshot. You can take a screenshot from that part. Okay, so I will post it in Facebook and in Blackboard. Sorry, I will put it in Blackboard, and we will make it like a home assignment. But remember, those home assignments, it's a simple. Each week we have some small home assignments. Maybe this is not the main home assignment for the course, because maybe we need to work with a data set. So this one will not be counted as a home assignment for the course, because we need to get 3 home assignments. So maybe this is a simple home assignment, maybe weekly home assignment, but not for the course home assignment. So it's like weekly home assignment. So because it's a simple one, but for the big home assignment for the course, please, you can just select a data set. It's up to you, by the way. You can just select. Try to search for a data set, and you can design your problem. Just select any problem which you want to solve. So I can give you a home assignment, or you can just decide by yourself which home assignment, which mini project I will use. So we can do it like this. You can just have freedom to just select any problem and data set, for example, and you can say, okay, I will work with images, I will work with text, I will work with a time series. So I can leave you to select, or I can select a home assignment for all people. So we need to decide this all together. So any other question for today? So should we stop here? Yeah, it's not obligatory. It's just if you have any solution, please just submit it. So I mean, for those weekly home assignments, maybe it's not very mature answer. For example, just upload it. It's not a problem. It will not harm anyone. Yes. So from last week, just upload it to Blackboard. So if you have any solution from any home assignment, please submit this one. Submit it. So it's not the big home assignment, but imagine it's a case, someone any conditions, any reason he cannot work on the large home assignment. So those small home assignments will be counted. We cannot say no for him, right? So it will be counted. So just please submit a report or a code or what you have done in this weekly home assignment. Just submit it, please. Don't leave it. Just submit it. Yes, of course. Yeah, we can do this. Of course, we can do this. But I feel that, I mean, each week for example, today, for example, in the home assignment last time, we have been talking about regression. Do you remember? We did regression today. So we solved it, in fact, right? So this one, we studied this adaptive linear unit, and we used it for regression. And this is a solution for regression. This one, correct? We had this one last time. I asked you last time to use a perceptron for regression, and we did it today, in fact. So in fact, those home assignment, I keep them in my mind, and I try to implement the next week. So this is the solution, correct? And we have the code here. It's for salary dataset. I remember that I asked you last time to build a regression model using a perceptron for salary dataset. So now we have it. So if you can go, Isaac. So if you can go to this example, it's the solution of one of the home assignments. And last week also I asked you to compare between different activation functions. We did that here, right? So we have those comparisons between activation functions. So in fact, those home assignment, weekly home assignment, I use it as like a starting point for preparing for next week. So I use those home assignment, and I try to answer it in the next week because they are important. So if you go through the lecture today and the code, you can see that we solved maybe the home assignment from last week. So you can check what has been done so far in your home assignment, your report, and compare it with the code which we did here in Colab. Yes, any other questions? Please just feel free to open your mic, and if you have any question, just so if there is no more questions, so we can stop here now, and we can meet again next week in the same time, in the same place. I will post a link for, a Zoom link for the new lecture, also maybe tomorrow or after tomorrow. And please, if you have any feedback, just send an email to me. Or just call me, for example, so we can discuss it. So thank you very much for joining me today, and let us meet again next week. And have a good week. And if you have any questions, just contact me anytime. Thank you very much. Bye bye.